Okay, morning and welcome back to the second day of the meeting. So we start off with Andrea Sander, who's going to be talking about hot star winds.
Mm-hmm.
Hot star winds.
Thank you. Can I get the slides? Oh, yeah. Thanks. Oops. Thanks a lot. Yeah, my name is Andrea Sander. For those who don't know me, I'm an Eminenta research group leader at the University of Heidelberg. So thanks very much for inviting me to give an overview talk about hot star winds here. So I will start with some general introduction. I guess I'm preaching partially to the choir here, but since this is a quite diverse audience meeting, let's start with the general aspects that stellar winds are basically ubiquitous in the upper HRD. And most of the evolutionary lifetime of massive stars is actually spent as a hot star. There's the cool star range is, of course, very important, and Emma Bisa will cover this afterwards. But my turn is to give you some overview about the hot stars, which have their flux maximum in the UV. So we see the appearance of line-driven winds, typically represented by spectral types O, B, and Wolf-Rayet. And the imprints are showing up in the spectrum, where particularly the UV range is, of course, interesting, where the flux maximum is. And we see this wonderful P-Cygni profiles. But if the winds are getting stronger, we also see emission lines popping up in the optical, and then the most prominent and usually one of the first ones to appear for hot stars is the helium-2 4686. So for hot and massive stars, radiation pressure really dominates. So we have a momentum transfer from photons to matter, and this absorption from this hot radiation is mainly in radial direction, while the re-emission can be in any direction, and this is how you get a radial net outflow. So if you put up the simple balance between radiation pressure and gravity, you can bring this down to three major quantities. And although hot star winds are subject to instabilities, there is the existence of time averaged solution, which is told you by the fact that if you look at a spectrum from a hot star and you do this a year later, usually it will not have major changes undergoing. And that tells you that at least there is a good deal with doing a stationary solution to a first degree and get the major stellar parameters out. So the interesting quantities here to understand the wind is, of course, the luminosity and mass ratio. And then there's this harmlessly looking opacity here, which actually is not so harmless once you study it in more detail, because what we have to talk about here is the so-called flux-weighted opacity. And if you compare that to the Rosselin opacity that you can get in nice tabulated forms, it really starts to deviate once you get into these outer layers of the star where the wind is launching off. And then the flux-weighted opacity can easily be an order of magnitude different from the Rosselin opacity. So this is basically the reasons why a typical stellar structure model, which is routing on these tabulated values, will not give you the outflow intrinsically, but has to prescribe the stellar wind with parameterized forms. So why is this difference? This is simply due to the short answer here in the context of the limited time that I have. This is due to Doppler shifting of the line. So essentially, while you have an intrinsically very narrow profile, the expanding layers allow you to sweep up all of this different opacity in a much wider wavelength range. Yeah, and then this can look very different for the different types of stars. So here's a typical case for an OB star, but you can also get like a double bump structure, for example, here in a Wolf-Rayet star. And there are various opacities involved. Of course, the major opacities are the bound-bound transitions, but also the free electrons are important. And then the bound-free and free-free transitions are very often neglected, but for certain objects, they can become quite important, and that might also be interesting in the context of this meeting and the late stages of some stars. So what shapes the wind parameters, it's really the contributions of the different elements. And here's an example for an O supergiant, the typical Zeta Puppis, which might not be so typical at all, but it's a very much investigated star, and you can see the different elements contributing to the radiative acceleration. But where the wind actually takes off, which is this zero line here, so this is acceleration normalized over gravity as a function of radius, it's the iron and the free electrons that bring you over the line, so that basically allow you to surpass this gamma equal 1. The thing is, if you look further, you can break this even down into the individual ions, and you will see a mess of these curves here. And I don't want you to follow all of them, but you can see that the different colors reflect to very different elements that contribute there. And this changes with regimes that you change. So even if you go down just 20 or 10 kilokelvin, you will see that these colors have changed and different ions are taking over to be the leading driver in the wind. So these regimes are really getting complex, which is why we need relatively sophisticated models if we want to study this in detail. And what you can also see is that at the launching point, it's usually the iron that plays the key role, which is the reason why the mass loss rate is so much dependent on the initial metallicity of the environment. And we will have talks later today by Grace and also by Elisa on low metallicity O stars, which will follow up on this more. Then the outer wind acceleration, so the terminal velocity is not determined by iron in all cases, it's determined here, but in other cases you really see a mixture of the different elements from various regime dependent things. So this is a complicated prediction and highly non-linear. For Wolf-Rayet stars, I showed you this double bump structure. This double bump structure is caused by the iron peak elements. So there you have a situation that's a bit comparable to what we discussed about the supernova and also the gamma ray burst yesterday, where you have this inner part that is optically thick and is not visible, but it's already moving quite fast. And that's what's happening in classical Wolf-Rayet stars, because they launch their wind here and then they get optically thin somewhere here where you have much lower ions, and this is then what you see in the spectrum. So this made it hard for quite a while to understand these objects. And what I'm doing in particular in my group is to use stellar atmosphere models to understand more about these stars. And here's the standard paradigm where we put in stellar and wind parameters independently, then do this whole machinery to get the emergent spectrum, and you can fit individual stars and you can predict ionizing fluxes and stuff like that. And then you can look, for example, at interesting objects that are in particular related to different types of supernova in the context of this meeting. So for example, supernova 197A surprised the community by being a blue supergiant, which was not expected at that time that these stars could explode. And blue supergiants, or in particular B supergiants, are still quite enigmatic. So one of my PhD students, Matthäus, has studied now a significant sample in the SMC. We know that they're evolved objects, but the raw HRD positions are quite inconclusive. So there's could be an extended main sequence. It could be helium burning mergers. And the combined UV and optical analysis allows us to give us more insights also on the chemical abundances. So for example, one thing that we derived is that we could derive the abundances, and then we tested the recent predictions from Athira Menon on the mergers, and we see that yeah, it's within error bars, but there's also a systematic shift. So it's still unconclusive of whether B supergiants are really merger objects or not. Some could be, and then in particular, the late type BSGs are more rare, and they could be hydrogen shell burning. So depending on what you put in your evolution models, you can actually find different solutions, and it's very, very hard to pin down the exact evolutionary status, even if you do all this sophisticated analysis. I know you're particularly interested in mass loss rates. So for mass loss rates, there's this long-standing prediction of Yorick's recipe by a significant jump when you go to cooler temperatures. We now have more and more insights that this jump might not be as large. It might also not be a simple downward trend, but something in the middle with a more moderate trend, which is closely described by the Kritichka, but also not perfectly described. And we now find this for different regimes. Later today, Olivier Verhamme will talk more about LMC B supergiants. Another interesting thing, I guess, in the context here is that the terminal velocity as a function of effective temperature is actually quite a good indicator, much better than the typical V infinity to V escape relation that we have from CAK, because the hard part there is to get the masses. While these two things you can get relatively nicely from the typical spectral analysis, and then you will see that the bulk of the stars follow such a trend, and then you have stars that are below this trend. So there is a bit of scatter here. It's not as nice and clean as we would like to have, but what we clearly see is that the stars below this trend, they have an enhanced mass loss rate, and that aligns with a lower terminal velocity. We will come back to this in a minute. Now, I'm working mainly with the power code, although that last one was a CMF-gen analysis. So at some point you might ask, there are different codes on the in the community. How similar are they? Can I trust results from one and put them together with results from the others? And we wanted to test that a bit more in the framework of the IAU collaboration. So I was coordinating the efforts for a blind test that we did with a lot of people involved. Where we just say, if everybody uses what they usually do, so not trying to benchmark the codes indirectly, but just saying, if you do what you always do on the same data, then what do you get? And we did that with 3 codes and 8 different methods. And what you get is a bit more spread than we thought, but generally in rather nice agreements. So we find effective temperature differences on the order of 3 kilokelvin, log G, differences typically on the order of 0.2, luminosity of 0.15 dex, and that's not so much the codes, that's more like what you do with the reddening of the stars and what you assume. And that consequence is that the mass loss rate, actually, if you do different approaches for reddening and clumping, can be varying by up to 0.4. So that's way more than a factor of 2. And this is something to maybe take into account. There's also an interest grown in turbulent pressure, which many of the codes have neglected so far in the hydrostatic regime, which might help us to reduce the famous mass discrepancy. But the bottom line is still, it's usually okay to combine results from different methods. Now, what I've shown you so far is the classic spectral analysis where you independently prescribe the stellar and wind parameters. And while this is nice to have a lot of free parameters, it's also physically a bit inconsistent because ideally your star should provide you with all the necessary physics to predict the wind parameters. And so if you want to do that, you can do something that is called a unified model for the star and the wind to get more consistent parameters. So essentially you remove this wind stratification from here, put it to this iterative scheme, and then predict it. It's a bit more challenging than I described here, but it's in principle what you get is you solve the hydrodynamic equation inside and outside. You get the velocity field consistency. You are no longer relying on a beta law. And by a boundary constraint, you also get your mass loss rate. For example, here the total opacity conversion. And so by this, you can actually predict the stellar parameters. And I did this a lot in the years. And now some of my PhD students are following up on this. So this is wind driving and mass loss rate from classical Wolf-Rayet stars. And you can get a recipe and then trying to get a reasonable description of that might look complex, but that closely maps the sequence of models here without just being a multilinear regression fit. So what we did here in this study for classical Wolf-Rayet stars, all launched by the Iron Bump, we find out that they scale fundamentally different than OB stars. Once the winds are optically thin, they have a surprisingly shallow trend, also with metallicity. It's just to the power of 0.3. But they have a strong L to M and metallicity dependent breakdown. So at some point you cannot maintain this strong mass loss and it really breaks down, and then you would probably go even too low here because the star would react in other ways that it wouldn't stay with the fixed parameters that we use in an atmosphere model. And then in the 2023 paper, I did a follow-up on the temperature or radius dependence. And what we found there is that there's really a crucial dependence on the critical radius, which you can roughly map with this T star temperature, but actually is mapped by the effective temperature at the critical point, which is unfortunately hidden to observations. So that's a very non-trivial thing, but it has a significant influence, and it will decide on how cool your star appears, because this is here the curve, what your radius is that you would naively observe, but this is the actual radius where you launch the wind. So the higher you go in mass loss, the more extended your star will appear because it has kind of a pseudo photosphere. Now, I talked about this strong breakdown, and this is interesting in the context, in particular, if you want to strip stars of significant masses. Because you can maintain this high mass loss reasonably well, this breakdown becomes, goes to kind of, can be avoided as long as you go to higher and higher masses. So this is a plot with mass loss rate over the metallicity. And what you see is that here at 12 or 13 solar masses, you already cannot maintain this for like half solar metallicity. But if you then go to 30 or 50 solar mass helium star in this case, you can maintain this much more downwards. So you can, in principle, make quite impactful objects at low metallicity as long as you can form helium stars of high enough masses. This nicely aligns with, for example, what Thomas did for the WN population. If you look into these and then you see the lower luminosity cuts, you see that the luminosity of the lowest known WN stars is higher and higher with lower metallicity, and that qualitatively aligns very nicely with this model predictions. Now, what do you do if you're going below the Wolf-Rayet regime. That has been quite enigmatic for some time, in particular between the classical subdwarf regime, where we know lots of stars, but most of them don't really have a significant wind, and the Wolf-Rayet stars. So there are, in principle, two types of stars: the compact stripped stars that Ylva Göthberg will most likely talk more about later today, and then there are what we now call bloated stripped stars, so stars that have been stripped of a part of their outer layer at least, but they are nice enough to hide in the OB star population, making us very hard for them to detect. And now in the framework of the Ulysses, my postdoc Varsha Ramachandran has found 3 of these objects, looking, for example, for these suspicious silicon 4 lines, which is usually a doublet, but if you see 4 of them, then you know you might have 2 stars there, right? And so in the paper, also part of the IGSHU series, for the first time, we have combined UV and optical spectra of 3 partially stripped stars, getting some ideas of the mass loss rates, which we find out here are much higher than the typical OB stars, but are lower than the typical Wolf-Rayet stars. So interesting enough, they align quite well with Yorik's 2017 prediction, despite having a bit different temperatures than assumed in these models. So there is a bit of scattering around it, but if you need to use something at the moment, that's kind of my suggestion. It's the best thing you can use in that regime, what is available on the market so far. Talking about multiplicity, yesterday we had this discussion about binary versus wind stripping. Thanks. Of course, binaries are important, but also it's not a either or. So binary stripping opens evolutionary pathways towards stronger winds. And then this higher L/M ratio that you get by stripping really boosts the mass loss rate. Yeah, Koshek has a poster on that for another example. And then for this optically thin winds, you get higher mass loss rates and lower terminal velocity. So don't always assume that a stripped star must have a high terminal velocity. If it has a high mass loss rate, it can have a much lower terminal velocity. So the late stage evolution could in particular boost that, because there you get an additional L/M boost during carbon burning and later on. Yeah. So multiplicity does not replace wind stripping. It might be necessary to explain, for example, WC stars, maybe even type 1c supernova, and we will have more talks on binaries and also on this connection later today. I don't really have much time to talk about very massive stars, so ask me if you're interested into that. But there is another type of Wolf-Rayet stars that is quite interesting, and that has this enhanced mass loss rates that are not covered in many of the current population models. They are starting to get into that, and that leaves some interesting connection to the endpoints about which Ethan will talk, I think, in today's afternoon session. In my group, what we're doing is we're trying to study some of these parameters with the idea to get better recipes on it. So for example, Roel is looking into this later type WNH stars. I haven't talked much about it, where we see that discontinuities in the mass loss rate appear close to the Eddington limit. Maybe there's even something like a bistability jump for Wolf-Rayet stars, which is probably metallicity dependent. And we're then also looking into other things like the galactic center stars. The Gautam, a student of Yorik, or now postdoc of Yorik, is looking into trying to get hydro models for R136, and Matthäus is also looking into B hypergiants, another very interesting regime close to the Eddington limit, which we hardly understand so far. So launching strong winds across different regimes can occur everywhere. It's not just a matter of getting a high mass necessarily. You can do this all the way from the low mass star range, which we discussed in a recent paper led by Jesus Stwala. And then you can compare these objects. I don't go into the details here, but even this white dwarf merger that I briefly mentioned yesterday, a PA30, aligns with this trend despite having an enormously high terminal velocity. So don't consider this 10 to the -4 that I saw in some plots yesterday as a hard limit. It's of course not the typical things you will reach with stellar winds, but depending on what you do, you can really get close to this limit, either with very high masses and luminosities, or if you just manage to launch your way far out in your wind far out enough, even at solar metallicities, you can do this, then at the consequence of relatively low terminal velocities. So with that, let me summarize. Radiation-driven winds are ubiquitous for massive stars. They're scaling with stellar parameters, in particular L/M, but also this critical radius, which is not usually accessible. There's a strong scaling with metallicity, with iron being the strongest driver. And then the winds are further enhanced when the objects get close to the Eddington limit. So for example, very massive stars, Wolf-Rayet stars, but also white dwarf mergers like PA30. And those winds could still be important in regimes where the typical OB star winds might no longer be very efficient, right? So that's interesting for low metallicity and the early universe in particular. So of course, there are still lots of open questions. It's why we have so much work to do. But multidimensional effects is something that we're trying to get a better handle on, which we want to include in our 1D models, because for the foreseeable future, we will not be able to do 3D models with all these detailed radiative transfer. The effect of radiation-driven turbulence on all of these predictions is something we want to investigate. And then regime changes due to ionization switches, where I alluded to what Rule and Matthäus are, for example, doing at the moment. And then, of course, the whole thing of the weak wind regime and the existence of a fraction of a hot phase. I didn't have time to talk about it today, but it's something to think about, that if you need more mass loss to explain something, don't always say it cannot be done by winds. We just don't understand what's happening in some of the regimes yet very well. Bottom line, none of the typical M dot descriptions was designed for the pre-supernova stage. They were all made for different stages, and I think we need to change that. We need something that is more tailored for the stuff that you guys are interested to produce the supernova. Thank you.
Thanks, Andreas. We have time for some questions.
Thank you, Andreas, for the very interesting overview on the winds. I'm curious myself regarding the differences in terms of models. What is sort of the main reason why there are differences between these models? Is it sort of in numerical implementations or something to do with physics?
What models do you allude particularly to now?
So you're saying sort of in the beginning half of the talk about the differences in, say, CMF gen and power.
Yeah, so for the spectral analysis, I guess it's a combination of both, and we will have to do a more thorough investigation to do really code versus code benchmark. We didn't do that here. We just did a method comparison. So there are different numerical things, but usually the physics in there are the same. So there's also a lot of things like how do you handle it? Which ionization stages do you include? What are you going to do, for example, with the iron ion blanketing, where you cannot include all the lines individually, and there are slightly different approaches on how you group the levels together. Is that a major influence? To be honest, I cannot give you final answers on that. And it's something not just me, but also the other people from the older generation who developed some of these codes are really interested to get into, and we will definitely follow this up once we have the proper resources for it.
Very nice overview, Andreas. Question about the stars that are coming close to the Eddington limit. Would there be a smooth transition then to the class of luminous blue variables? What would be the difference between an OV star that is close to the Eddington limit and a classical LBV?
That's a very good question. We're trying to get to this regime with models to understand that. And I would say what we see in the normal OF to WN transition is rather smooth. For the LBVs, I'm not so sure, because we are also hitting a regime where we have, for example, helium recombination or even hydrogen recombination. And that is a significant amount of opacity that in a stationary model is also causing troubles. And maybe nature is elegant in that sense, that it causes some turbulence or so, which could smooth this whole process and then make it a smooth transition. But I wouldn't vouch for this. So there might be hard limits also where we see fewer stars. And that could be something where like the wind connection is not that easy as we usually want to prescribe it.
Yeah. I have two questions. One is this mass loss rate of the Wolf-Rayet stars. These are evolution of time, right? So what is the range you expect, like when the stars evolve, or is it like, what is the phase in which you give an idea of the mass loss?
You mean the mass loss rates for the Wolf-Rayet stars, that they should change over time?
Yeah.
They should, but not so much due to time. But what we want to do ideally is, of course, a parameterization of the fundamental stellar properties. So a Wolf-Rayet star that loses a lot of mass and is stripped of their outer hydrogen layer will essentially go down the helium main sequence. So you can just use this prescription, which as a function of L and M, and then you will get a proper thing for the whole main core helium burning stage. What is not covered there easily is if you go to the helium shell burning stage or so, where you suddenly have a different luminosity to mass ratio. So that's something that would need another set of models.
Okay, and one more in quick addition to that. So when we do this modeling of, you said that winds could produce like mass loss rates like that. But we assume different, like instead of rho proportional to r to the power minus 2, some other exponential forms of the medium when we do this modeling, our modeling. So how do you physically explain those cases? Like if it's any other exponent when we try to explain for these stars.
To be honest, I haven't investigated that too much. So of course, the density will depend on what we would find for the typical wind velocity law. And if you have other impacts like a turbulent term, then the radius dependence from that would essentially propagate into an extended gas pressure term could be slightly different. But we haven't done too much stuff in that phase. So maybe we should talk afterwards.
Yeah, sure. Thank you.
Okay, I think we have to move on now. So let's thank Andreas again. And our next speaker is Emma Besor, who is joining us via Zoom. So it might just take a moment or two to get her up.
The talk's been pre-recorded, but I am here for questions afterwards, so you should have a video.
Thanks, Emma.
Hi everyone, my name is Emma Besor and I'm the Bock Fellow at Steward Observatory over in Tucson. I'm really pleased to be joining you, albeit virtually, for this really interesting session. So I'm very happy to be talking to you about red supergiant mass loss and evolution. So just to take it back to basics for a minute, red supergiants are evolved massive stars with initial masses anywhere between 8 to 25, 8 to 30 solar masses, and they are the direct progenitors to type 2 supernovae. So knowing which ones explode and which ones don't explode is a very powerful test of stellar evolutionary theory. So on the HR diagram, the red supergiants are the ones in the top right hand of the corner, so very bright and very cool. And we live in a really great time because we have seen red supergiants explode as supernovae, and we now have enough archival imaging that when a supernova goes off, people can hurry through the HST archives and identify potential progenitors. So this figure in the middle shows a supernovae, and then the authors of this work went back and identified a progenitor. So you can see in the left-hand image a little red star, and that is the potential progenitor. And then you can wait, if you're very patient, for the supernovae to fade away, and you can confirm that the progenitor candidate was in fact the star that exploded. And this is the most direct method of linking supernovae to their progenitors. But it's not enough to just say that we see these stars explode. We need to know more information about the star. Specifically, we need to know the luminosity of the star and perhaps even link it to the initial mass. So it's actually quite difficult to do this because that figure I showed you was a very nice example where there were multi-band images. So we had a nice color, we knew it was a red supergiant, they knew the temperature. But in reality, you'll probably only have one photometric point from the pre-explosion, and it might even be an upper limit. But nevertheless, you can take this pre-explosion photometry and you can make a few assumptions. So if you only have one photometric point, then you need to assume a temperature, a color, or a bolometric correction and work out the terminal luminosity of the star. And then you can take this terminal luminosity and use an initial mass terminal luminosity relation, like one shown on this figure on the right, and use that to determine an initial mass. But as you can see, there's a lot of assumptions. You have to assume a color, you have to pick the right, or the right, air quote, initial mass final luminosity relation. So there are a lot of uncertainties, a lot of places to potentially introduce error. So while it is the most direct method, it is by no means perfect, and that's how you end up a lot of the time with huge dispersions in the initial mass or the luminosity determined. This came up yesterday, I think, in discussions about the progenitor to IXF. But people do this, so work out luminosities and initial masses for supernovae progenitors, and very famously it was done in 2009 by Stephen Smart and his group. So the Smart 2009 paper, they gathered as many progenitors as possible with pre-explosion imaging and determined the initial mass for each of them. So this is what they ended up with. It's kind of a cumulative distribution. And if the population of supernovae progenitor masses followed what we see for red supergiants in the field, you would expect it to follow this solid green line here. But instead, what we see is a much steeper relation. So we actually don't see any progenitors in this sample above an initial mass of around 17 solar masses. So just to quickly caveat, this does need to be updated. There have been a few more type 2 supernovae gone off recently, including IXF. So this figure is quite a bit out of date now, but it does illustrate the point. So the question is, why are we not seeing any stars in this shaded region explode? What is happening to the highest mass, the highest luminosity progenitors? And one thing that has been suggested to solve this issue, this discrepancy, is perhaps to do with the mass loss rate that happens to stars in the red supergiant phase. So we already know that the type of supernovae we see does strongly depend on mass loss. So you have two kind of classic options. So for lower initial mass stars, so the 8 to 30 kind of region, you would expect the star to leave the main sequence and end up in the red supergiant phase. This star would then hold on to its hydrogen envelope, so it wouldn't have hugely strong mass loss, and it would die as a type 2 supernovae, so a hydrogen-rich supernovae. The second kind of classic option is for hot progenitors, so stars of a higher initial mass. So these stars actually never reach the red supergiant phase because their mass loss rates are too high from the off. So this means that they just lose all of their hydrogen envelope really quickly and they never reach the cool region of the HR diagram, and they die as type 1 or hydrogen poor supernovae, so 1bCs. But a third option was suggested to kind of solve this red supergiant problem. So the suggestion is that maybe these stars, the higher initial masses in the red supergiant phase, the 20 to 30 kind of region, perhaps they reach the red supergiant phase and then undergo very, very strong mass loss in this short phase and lose enough of their hydrogen envelope to have it be completely removed to force them to move back to the hot side of the HR diagram and die as a different type of supernovae. So this, you can see all of these effects in stellar models. So these models are from 2000, and these are the Geneva models from 2000. And in these models, you can see that a 25 solar mass star reaches the red supergiant phase and dies there. The 60 solar mass star, for example, skips the red supergiant phase, goes straight to the Wolf-Rayet phase, and would die as a hydrogen-poor supernovae, so as the kind of classic options laid out. But if we look at stellar models from the same group, but a few years later, you can see a kind of different story. So in these models, the 15 solar mass stars reach the red supergiant phase and would die as a type 2 hydrogen-rich supernovae. They hold onto their envelope. But above this, the 20 solar mass star now has a very short red supergiant phase before losing all of its envelope and coming back out and dying as a different type of supernovae. That moves the maximum initial mass for stars that we would expect to see as type 2s all the way down from like 30-ish down to about 20 solar masses, or somewhere between 15 and 20 solar masses. And these models are from the same group as the previous slide. And obviously, stellar evolution models get updated all of the time. So we get new information about abundances, opacities, core overshooting. But importantly, in this case, how mass loss rates were implemented changed quite significantly. So it's important to know how mass loss rates are actually implemented in stellar models because it's not worked out from first principles. These models all rely on prescriptions. So for a given luminosity, there is a given mass loss rate depending on the prescription that you're using. And it's generally split into two phases. So everything above 10,000 Kelvin has a hot star prescription. So the most commonly used one is probably the Vink prescription. And below 10,000 Kelvin, you're in the cool supergiant regime. So you use a cool a cool supergiant prescription, such as the Diaga prescription or the Van Loon prescription. And I will talk more about those prescriptions specifically very, very soon. But importantly, in the updated Geneva models, so those 2012 models, if the luminosity of a star went above 5 times the Eddington luminosity, mass loss rates were cranked up by a factor of 3. This kicked in at around 20 solar masses. So now you can see why that star that previously would have died as a red supergiant now lost all of its envelope in the red supergiant phase and died as a different type of star. But the important question to ask now is this increase in mass loss rate by that factor of 3 justified by observations? Okay, so just to go back to the prescriptions, in the cool supergiant phase, the prescriptions are purely empirical, and there are a lot of prescriptions to choose from before you even get started with your stellar models. So you can see here on this figure a bunch of different cool supergiant mass loss rate prescriptions, and depending on the prescription you pick at a given luminosity, you can end up with quite a different mass loss rate by a factor of a factor of 10 or more. But generally, modelers like to use the Diaga 88 prescription. But if we look at that prescription on its own, even that has like a large amount of scatter, so plus minus a factor of about 10. So that could be the difference between a star losing all of its hydrogen envelope or losing none of it at all. And it's important to dig into where the Diaga prescription came from because it is so widely used. So it was a literature study, so the authors collected mass loss rates for 271 stars across the entire spectral range. So basically, if there was a mass loss rate and a luminosity in the literature, they collected it and they came up with this mega mass loss rate prescription for every single star. But this prescription is actually no longer used for hot stars, it's only used for cool stars. And for red supergiants, it actually only contains 15 red supergiants. These are mostly kind of famous and bright galactic sources, so it was just things that had already been observed. So they were very limited in what they could put in their sample, it was just what data was out there. And many of these stars have actually had their luminosity significantly revised since the days of this paper. So just to show you, so the red points are all the red supergiants in the Diaga prescription, and the ones that had updated luminosities, a lot of them came down by quite a significant amount. And another important thing to note is that over half of the stars in the Diaga sample have luminosities above a log L of around 5.2. And for comparison, in the LMC, only less than 12% of red supergiants have luminosities in this kind of range. So it's a very skewed sample. The big part of my work is to come up with a mass loss rate prescription that is a more reliable sample of stars. So we targeted red supergiants in clusters, and the reason we did this is that if you look at red supergiants in clusters, you can assume that the stars probably have the same metallicity. If it's a coeval population, they probably have the same initial mass, and you probably have a better constrained distance since the stars are all in clusters. It's easier to get distances and therefore more reliable luminosities. So we used a lot of mid-infrared data. We used data from Sphere, Spitzer, WISE, MSX to name a few. And we worked out mass loss rates and luminosities for every red supergiant in our sample. And this is what we ended up with. So each symbol is a different cluster. So we have different luminosity mass loss rate relations. And what we found was that all of the clusters had the same gradient of this relation to within the errors. So we simply fixed it. And we found that as well as this, so you can see the gradients are all the same here, but we also found that the offset of the relation increased with the initial mass. So those stars on the right are from RSGC1, and they are the highest mass stars. So this allowed us to determine an initial mass dependent mass loss rate prescription rather than just depending on mass loss rate and luminosity. When we compare this new prescription to the Diaga prescription, we find that we have a reduced scatter. So The new prescription is the figure on the left, and the Diagra prescription is on the right. So you can see there is a smaller scatter. There's still some scatter, of course, but it's much reduced. And also we see a reduced offset. So while the average offset for the Diagra prescription doesn't maybe look that bad, it's like 0.18, so that's a slight overestimation of mass loss rate. What we do see is that for the highest initial mass stars, so the blue squares in this case, the highest luminosity objects, the mass loss rate's overpredicted by a much higher factor. And this is important because these are the stars whose fates are the most uncertain. They're the ones where we don't know which kind of supernovae they're dying as. So it's really important we get this nailed down. So if you compare the mass loss rates for what we determined to what is currently inputted in Geneva, we find that a 20 solar mass, the Geneva models find that a 20 solar mass star would lose something like 10 solar masses of material, and that's what's forcing the star back to the blue. Whereas we find a star of this mass would only lose around 1 solar mass of material, and that is not enough to get the star to move back to the blue of the HR diagram. So there is no evidence for enhanced mass loss. So there's no need to crank up the mass loss rates by a factor of 3. And what this means is that mass loss rates cannot explain the red supergiant problem. So the question I always get asked is, what about high mass loss rate phases? And it's a fair question because the mass loss rates that we're measuring with the mid-infrared XS are not instantaneous. So we're sensitive to the warm dust, which is within a few hundreds of years. But we look at red supergiants in clusters, so we can kind of see how the mass loss rates evolve as the star evolves. But if there was a high mass loss rate phase, we would need it to be able to remove around 10 solar masses of material. And we estimate that 10% of red supergiants should currently be undergoing mass loss rates above 10 to the minus 4 solar masses per year to allow stars to move back to the blue. So we set out to look for these high mass loss rate stars in the LMC. And this has been done kind of before. So the Van Loon sample of red supergiants are the dust enshrouded red supergiants. So this study claimed that there is a short-lived high mass loss rate phase that all red supergiants pass through. This was also talked about in the Goldman 2017 paper. So that's that blue circle above the Diagra prescription. So we set out to look at the red supergiants in this sample. So the ones that are in the Van Loon prescription are the ones that we've highlighted with red stars on this figure. And you can see that compared to the rest of the stars in the LMC, they don't appear to be a unique group. You might expect that all of the dust enshrouded stars would sit to the top right, and they do kind of a little bit, but there is a little bit of scatter in there. There's also some weird object to the right, which doesn't look like a star, so we're just not going to worry about that for now. But this is what we think the dust enshrouded red supergiant should look like when you look at its SED. So it should be very bright in the mid-infrared, and it should have a noticeable reduction of flux in the optical. So that's where the dust is absorbing a lot of light. So this is what we were looking for through that whole sample of LMC stars. And what we find is that actually no, not really any red supergiants in the LMC look like this. There's one exception. There's one star that lies in our region of what would be considered a dust enshrouded red supergiant. That's WOHG64. And this one is a known weirdo, so it has a really weird dust shape. It's got lots of funky stuff going on, so I wouldn't use this one star as a benchmark for all red supergiants. It's really weird and probably not indicative of some dust enshrouded phase. And you can see here how weird it is. It has an extinction significantly different to the rest of the stars within the LMC. So if there is a dust enshrouded phase, it must be very, very short-lived, even shorter than 10% of the life. So it would not be able to remove enough envelope to force stars back to the blue of the Hertzsprung-Russell diagram. And what this means is that there's probably no single star route to strip stars in the 10 to 30 solar mass range. And above this, most stars are in binaries, most massive stars are in binaries. So maybe this means that there is no single star route to stripped stars at all. Maybe this is a phenomenon that only occurs when there are binary companions or multiples within the system. So to put this in context of supernovae again, the observed hydrogen-poor supernova fraction is about a third of all the supernovae. And if you do a back-of-the-envelope IMF calculation, stars between around 8 to 30 solar masses make up around 85% of all the massive stars. Stars above 30 make around 15% of all the massive stars. If mass loss rates were higher, you could explain this discrepancy because you would expect the upper limit for type 2 supernovae to be lower, so the stars in the 8 to 16 range make up about 60% of all the stars, and stars above 16 solar masses would make up about 40% of stars. So that could kind of explain the hydrogen poor, hydrogen rich fraction we see. But what we actually find is that mass loss rates are lower. And again, I reiterate here that single star evolution cannot explain the observed supernovae rate. And that is strong evidence for the most hydrogen poor supernovae being the products of binary interaction. And I'm aware that I am now out of time, so I'll leave up my conclusions. And even though this is pre-recorded, I am in the audience, so you can ask me any questions. Thank you for listening.
Thanks, Emma. Do we have any questions from the audience or online? Yeah, Yorick, online.
Yeah, hi Emma. Interesting talk. On the issue of the initial mass, you have a mass loss recipe that depends on the initial mass, but the initial mass of the star doesn't set the mass loss rate. It's the current day mass. And there are these interesting observations from the Bananas group where there's a kink in the mass loss rate with luminosity. And if that is the kink that we also see in hot stars, we expect it to be gamma dependent. So there should be an inverse mass dependent. So you expect a kind of a runaway because the mass and the luminosity in the red supergiant phase are basically decoupled. So if you lose mass, the luminosity doesn't drop and you can keep creeping up the mass, which is exactly what is needed to explaining something like Humphreys-Davidson limit. So I wonder, should we not depend our mass loss recipe on the current day mass, which of course we can't observe, but isn't that the physical thing we need?
Yeah, so it would be useful if we could measure the current mass, but I think that what we're seeing is, red supergiants will arrive at the red supergiant phase at a higher luminosity if they're higher mass with less dust. So that's what we're observing here. On the kink that you see in the Bananas group, I think a lot of that is probably to do with contamination in the sample because they go to quite low luminosity. So there's going to be a lot of AGBs mixed in there that have a different mass loss rate mechanism because they're dust-driven winds. So I think that probably has a lot to do with like pushing the bottom end of the relation up. So I wouldn't consider it to be the same as like the hot star kink at the minute.
Right.
I think Stuart, you're first. Hi, Emma. Nice work. I might have missed it, but the study of those 6 clusters, what was the actual diagnostic you used to measure mass loss rates? And is there still some dispute about how reliable a lot of these indicate diagnostics actually are?
Yeah, so we use the mid-infrared excess to get mass loss rate. So we fit dust models to the data and use radiative transfer models to work out a mass loss rate. We have to make assumptions such as, the gas to dust ratio and the wind velocity. So there are some errors in there. One of the clusters, that RSGC1, has also had its mass loss rates worked out using radio, and they also showed these kind of lower mass loss rates, which is, a completely different method to get mass loss. So a lot of the methods are kind of converging now, but there are definitely errors with all of them, assumptions all along the way. But at the moment, this is like quite a direct way of measuring mass loss rates.
Hi, Emma. Thanks for the nice talk. This is Daiji Hiromatsu from Harvard CFA. So I was wondering about the single stars between 20 to 30 solar mass range. So if they don't lose much of the envelope, I think they're going to die as a type 2 with a really long plateau, which we don't typically observe. So what do you think about what's going on there?
Yeah, so I think there are other there are other things that could quench the kind of like plateau length, right? Like it's not just dependent on the on the on the initial mass. It could be to do with like explosion energy. So one thing I'm hoping to look into is seeing how you could maybe like hide these long plateaus, like what could be stopping us from seeing them. But it could also just be that, a lot of models have used the old Diaga prescription, so we've not really got a set of progenitor models with realistic mass loss rate recipes in them. So it's definitely something that we need to like explore and see like what effect that has on like what we determine for initial mass from maybe plateau or other supernova diagnostics. But yeah, that's a good point. There might be ways to hide a long plateau, because I agree we haven't really seen that many of them.
Hi, Emma. Tomer here. Thanks for the nice talk. I have a question about the dust enshrouded phase. So you say that it is rare. It must be very rare because you only observe one of these objects. But if you compare it to only the population of red supergiants, which exceed 20 or even 25 solar masses, it doesn't look that rare anymore, right? So what if those objects go through this phase?
Yeah, I see the point you're making. I think that an issue we have in massive stars is like low number statistics, right? And people tend to point to a weird star that may have something else going on with it and say, oh, well, they must all do that. And I think at the minute it's too premature to do that. Like we only have that one weird object, and there's a lot of evidence that it's not a normal single star. It's got a lot of odd stuff going on. So I think it's dangerous to take a one weird star and be like, oh, maybe that's indicative of like this broader phase. But yeah, that's just my opinion on it.
Okay, so let's thank Emma again.
Thank you.
And we move on now to Mu-Kyun Young, who is talking about 1BC supernovae.
Hello, everyone. I'm Mu Jung from Seoul National University, South Korea, not South Africa. And I'm working with Sang-Chul Yoon. And today, I'm very thankful for you to having a great opportunity to talk today. I'll talk about effects of winds on the optical and near-infrared properties of type 1b and 1c supernova progenitors, especially focusing on how three space telescopes, the Hubble, James Webb, and the future Nancy Grace Roman can be used to detect and investigate the progenitors. Supernova progenitor study is important key for late-time evolution of massive stars, and how they evolve and what determines they explode or not. But until now, we only rely on the follow-up observations for the detection for the progenitor properties. However, the most certain way is directly detect the progenitors from pre-explosion images like left figures. Until now, Hubble, during last few decades, detected amount of type 2 supernova progenitors like this, but for type 1b and 1c, we only have 3 progenitors or candidates yet. It means progenitor of type 1b and 1c may be fainting the optical to detect. And we will discuss the reasons here. First, as shown in this figure, the exact mass is only about 1 to 4 solar mass ranges, and the resulting progenitor mass is much less massive than current known galactic Orpheus stars. And next, type 1b and 1c supernova do not show hydrogen features, and it means their progenitors should be fully or almost fully stripped and reveal their hot and compact core at the surface. Under the black body assumption, type 1b and 1c it is clear that these stripped supernovae progenitors are fainting the optical. Then is it not impossible to detect the progenitors with current instruments? Then how can we explain the 3 directly detected type 1b and 1c supernova progenitor candidates. We need to think about the possibility of optical sequence of type 1b and 1c progenitors. In this study, we will check the detectability of Hubble, James Webb, and Nancy Grace Roman for type 1b and 1c supernova progenitors and constrain their physical parameters like this. And we will also discuss the advantage of near-infrared observations compared to optical. We adopted the progenitor models from June 2017 and 2019 and constructed the spectral models from using radiative transfer code CMFSEN. We also assumed the various wind mass source parameters of 0.1 to 10 times of Fisher value to cover the uncertainty of wind density. This is an example of type 1c supernova progenitor spectra and showing how if optical sequence can affect their spectra. First, photosphere forms far from the stellar surface and with a relatively low effective temperature, and hot and ionized winds make strong free frame emission and line emission features. Therefore, these effects of winds make the progenitors be bright in the optical compared to the blackbody assumptions in dotted lines. Moreover, therefore, the higher mass source ring models with lighter colors have higher optical luminosities than compared to the lower mass source ring models with bluer colors. And this effect is much more significant and prominent for type 1c progenitors since they are more compact and hot. And therefore, type 1c progenitors may have similar or even brighter optical luminosity than type 1b progenitors. And we have to notify that the effect of winds may be significant even in near infrared and brighten the near infrared luminosities. So first, let's go back to the optical. Then if the 1b and 1c progenitors are not that faint in the optical, then why Hubble cannot detect the most of progenitors? It is because the short exposure time of pre-explosion images of about less than 20 minutes. The dashed lines in the right figure is showing detection limits of supernova pre-explosion images, and most limiting magnitudes are not deep enough to detect the physical mass source ring models in black colors. It means for those cases, Hubble only can give the upper limit constraints for the mass source ring of progenitors or possible companion masses. And for directly detected cases, their progenitors may have exceptionally high mass source rates or massive companions. And I didn't show these results here, but IPTF 13 BVN and 2019 YVR are maybe those cases. So we have other two near infrared instruments now. One is the James Webb, which are giving us nice images with higher spatial resolution and deeper limiting magnitude than Hubble. And the other is Nancy Grace Roman, which will give amount of pre-explosion images of supernovae with about 100 times the larger field of view than Hubble and James Webb. Oh, sorry. Then, which instruments will be the best, will be most effective than to detect the progenitors? And how long exposure time will be needed to detect the progenitors? These three figures are showing the detectability of Hubble, James Webb, and Nancy Grace Roman. And each dashed line is showing the detectable magnitude if the progenitors are in 50, 20, and 10 megaparsec distance. If we are not considering the extinction, Hubble has the best detection possibility, and James Webb and Roman are less. But we need to consider the extinction, of course, because most of type 1b and 1c supernovae are observed in highly obscured region. The median V filter magnitude is about 1.3, and 1/3 of them are higher than 2 magnitude, so we need to consider. After adjusting the V filter magnitude of 1, then James Webb is the best, and Roman follows, and Hubble was the worst. So James Webb and Nancy Gray instrument and near-infrared instruments have advantages in detecting type 1b and 1c supernova progenitors, and we have to notify that this result is under the 1 hour of exposure time. It means 1 hour of exposure time with James Webb may not detect enough to detect the type 1bc progenitors in 20 megaparsec, and longer exposure time may be needed. And from now on, we will talk about more additional advantage of near-infrared observations. First is for type 1b progenitor with extended envelope in orange circles. In optical, their magnitudes are very slightly changes by changing their mass loss rates. But in near-infrared, their changes are much more significant, and near-infrared magnitudes can give much better constraints for their mass loss rates. Moreover, sorry for inconvenience, in some infrared color magnitude diagram, type 1b progenitor with extended envelope and compact 1b progenitors are well distinguished. I told you that in some colors, because in some colors, in nearby colors, there can be some ruined by strong emission lines. So some colors cannot be used. And also there is another advantage is the progenitors and possible companion background stars are well distinguished in the near-infrared or with near-infrared magnitudes and colors. For optical, OB type stars, which can be a companion or background stars, have comparable luminosity to progenitors in the optical, but in near-infrared, they are much less luminous. Moreover, in some color diagram in near-infrared, they are well distinguished, but in optical, they are very confusing. Also, not all colors can be used, but some selective. This is my summary of talks, and thank you. And I'm looking for your comments and questions. Thank you.
Thank you. Do we have any questions? If not, I have one I wanted to ask. So it's really nice seeing the comparison between JWST and Roman.
Yeah.
And of course, one of the problems with JWST is the overheads are horrendous. So, just for pointing the galaxies. So I wonder, did you look at, if you're doing a survey and you're trying to maximize the number of galaxies you observe, how that factors in?
Yeah, very hard. We need to have some stretch together for the progenitor survey, I think, but I'm not clear now. Yeah.
Do we have any other questions or online? Anna?
Yeah, nice talk. So I just wonder if you have any comments on detecting these progenitors with the ELT class telescopes.
ELT?
Extremely large telescopes.
Oh no, I didn't calculate it with that.
Okay,
yeah,
I think it would be interesting.
Yeah, I'll investigate that.
Right,
thank you.
Thanks.
Okay, so thank you again.
Thank you very much.
And our next talk is Olivier Verham, who's online, I believe. Yeah, video.
Hello, everybody. My name is Olivier Verhamme. I'm going to talk to you about how we used UV and optical spectroscopy to show the suppressed mass loss rate of these supergiants in the LMC in this case. First off, I want to thank the organizers for allowing me to speak, even though I couldn't be there physically. Really appreciate it, but I should be present in the Zoom to answer any questions at the end. Let's talk about why we care about these mass loss rates in this mass regime or in this luminosity regime. Well, it is because it's such a big influence on the actual evolution of these stars. This is a MESA model. These are two MESA models, I suppose. Twice the exact same MESA model. Only thing that we changed, or that the Björklund et al. Group changed, was the mass loss rate. In the dashed line is the standard MESA mass loss scheme, and in the full line they suppressed the mass loss rate quite a bit. Now, what you see is that you end up with a completely different end result. In the standard regime, you see that you end up with some sort of Wolf-Rayet star of 23 solar masses, but in the suppressed mass loss case, you see that you end up with a way heavier star, almost double the mass. And it's not even close to looking like a Wolf-Rayet star. It still has this envelope. It's not hot enough, not even close to hot enough. So it's a completely different star. And stuff like this, the fact that we cannot be certain how our single Wolf-Rayet stars form until we actually have a good grasp on the mass loss rate, but also the masses of our black holes we find, how supernovas react, is all going to be dependent on what happened in this region and this period of time where they lose a significant amount of mass. Even in the suppressed mass loss rate scheme, they still lose a lot. So what's actually the difference between these two mass loss rate schemes? Well, if we look at this plot here, we see the mass loss rate over temperature, and the red one here is the typical Vink scheme, which is the standard in MESA. It's part of this Dutch scheme, and this Vink prescription is characterized by this jump upwards at 25 kilokelvin, this discontinuity, which is called the bistability jump. It is an increase in mass loss rate thought to be caused by the recombination of iron 4 into iron 3. So what happens is iron 4 recombines into iron 3. Iron has a lot of lines, and because these are radiation-driven winds, they're actually pushing against these line transitions, you could say. And because you add a lot of extra line transitions, the wind should become more efficient, and that increases the mass loss rate. That's the idea here. More recent modeling efforts, however, did not find this increase at all. The Björklund see pretty monotonic decrease, and the Kritichka rates find a localized bump, but at way lower temperatures. And this suppresses the mass loss rate by quite a bit. So my goal is to figure out if this bistability jump is real or not by figuring out the mass loss rate of stars around this 25 kilokelvin region. And figuring out if they're either here or here on this diagram should be pretty easy, even if we get relatively large error margins. Now, I'm not the first person to try and do this. You have Markov and Pols from 2008, you have Rubio Diaz from 2021, you have De Burgers et al. From 2024, who all looked into this as well. And they did not find this jump upwards. So what's the difference between me and them? Why am I retreading their work? Well, they only had access to either optical data or continuum data, while I have access to spectroscopy in both the optical and the UV, thanks to the Ulysses program and the XUTU collaboration. That's what I'm showing here in the blue histograms, is the amount of B giants or B supergiants and bright giants I have in this temperature regime based on their spectral type. And why it's important to have this extra UV data is because if you only have the optical data, your mass loss rate is determined almost singularly by the H-alpha line. The H-alpha line could look something like this if you have a clumping factor of 40 and a mass loss rate of 8 times 10 to minus 8. The clumping factor here tells you how dense the dense regions of the wind are compared to the average. And the H-alpha line is notoriously degenerate with mass loss rate and clumping factor. And I can show you this because if I decrease the clumping factor to 1, meaning I have a smooth wind now because the densest regions are equal to the average, and I just increase the mass loss rate, I can get an H-alpha line where the peak is relatively consistently at the same height. Now, if this was an optically thin model, I could get the exact same line out, but this is not. So the onset of clumping and so also influences it. I could fine-tune the parameters to get the exact same line out, but I think that's not necessary. The fact is that if you only have the optical data, you pretty much only have the H-alpha line to look at mass loss rate, and there is a degeneracy there between the clumping factor and the mass loss rate. The way you can break this degeneracy is if you look at, for instance, resonance lines in the UV, which react differently to this clumping factor. They have a different dependence on it, and you can see that the lines we get out in the end are completely different. There's no confusion here. We can see that there's a higher mass loss rate here due to the deeper troughs and the higher peaks. So this is the goal here. I want to do this again, this look, but without the uncertainty if the clumping factor change is there as well in the bistability jump. That's the goal here. That's the new thing I'm adding. Now, I've talked about a couple of parameters we need to look at. We've talked about temperature, clumping factor, mass loss rate, but we need a lot more. In total, we need 18 parameters at once to be determined. And to do that, we use Kiwi GA or Kiwi GA, which is a GA, genetic algorithm, that uses fast wind to compute its synthetic spectra. Real quick, how a GA works is you start with a random guess of models, about 100. You compute the fast wind model, the synthetic spectra for all 100 of them. You look which ones are doing well and which ones are doing bad. You take the good fitting ones, obviously, and you allow them to interchange. So you take some parameters of one, some parameters of another, and now you have a new generation of models. Now, before you actually compute synthetic spectra, you allow mutations, small changes in the parameters to happen. This is important because we want to make sure that we're actually exploring the parameter space further, and we don't want to get stuck in local minima. So these mutations, these small changes are very important. And you do this in a loop until you're happy with your result in the end. Now, let's look at the actual results. The stars I'm looking at range from 33 kilokelvin to 15 kilokelvin. They have a mass of about 15 to 55 solar masses, but this is spectroscopic mass, so take it with a grain of salt. And in the actual paper that's now been accepted, we actually talk a lot about the clumping factor and so on as well. But here I will mainly focus or only focus on the massless rate. And this is what I'm showing you here. You see on the y-axis the massless rate, on the x-axis the temperature, and the color is showing you the classical Eddington factor, or classical Eddington limit, whatever you want to call it. And this is showing you luminosity over mass. So this is showing you how hard the radiation is pushing compared to the mass is pulling. And what I'm showing here is a pretty monotonic decrease with temperature and also a gamma E effect, which when you have a low gamma E, you also have low massless rate. This is to be expected. What we do not see is a sudden jump upwards. But this is quite hard to say a lot about because what we're lacking here is the influence of the mass and luminosity separately in these prescriptions. So to get that into account, I looked at the mass, luminosity, and so on, all the parameters I need to put into prescription that I derived from my observations, plug them in the prescriptions to get their massless rate out, and then I divide that by my empirically found massless rate. That's what I'm plotting here. On the y-axis, you have this division from the prescription to the empirical found massless rate. On the x-axis, you have the effective temperature, which means that on the one line here, that means a perfect agreement between prescription and observation. If it's above it, it's overestimating. If it's below it, it's underestimating. What you see is that on the hot end, all models do relatively well. The Björklund, Fink, and Kritichka models all do reasonably. But once you get at the bistability jump region, you see that the Fink rates start to increase like crazy because that's how they've been programmed, right? They need this shot up. And this is exactly what you see here. They go up. And there you see that they overestimate up to a factor 100 once you get down to like the 18 kilokelvin range, right? This is this sudden jump upwards. The Kritichka and Björklund rates, on the other hand, do seem to agree a lot better with the actual observations. The Björklund rates underestimate by a factor 2 very consistently, but the average offset of the Kritichka rates is also about a factor 2, but they seem to over and underestimate depending on the model. So they seem to be very close. Now, what I want to highlight here is that we do not have looked, or we did not have the opportunity to look at this bump we showed at the beginning from the Kritichka rates, because this bump is way too cool for a sample. It's even cooler than this 15 kilokelvin range, and it's too localized. So to get a good grasp on what's happening there, you need very good precision on both massless rate and temperature. And temperature is not that hard to get a good grasp on, even in that lower temperatures. But once you get low in massless rate, which we expect at these low temperatures, it's very hard to get a good grasp on the actual massless rates there observationally. So yeah, I want to then highlight again that I think the evolutionary models that we're using right now are using massless rate prescriptions, which do not seem to agree with the observations at the moment. That's not just me saying that. We've looked at the other papers which have the same conclusion, even though they cannot take into account the clumping. If you want to know more about how this clumping behaves over temperature, please take a look at the paper that's been recently accepted. Thank you all for listening.
So we have some time for questions. Or online questions as well, if anyone has one. Yeah, well, if there's no questions online, I'll ask one. So what mass loss prescription should we use then?
I think Andreas also talked about it, but I think that the most logical one at the moment would be the Kritichka one, I think, because if we look at the different studies that have been going on using this XUTU collaboration, I think consistently they have been performing well, even at the slightly cooler end where the Björklund ones start to underestimate too much. They drop off too steeply, while the Kritichka one seems to do better there.
Okay, If there are no more questions, let's thank Olivia again. And next up is Grace Telford, who's talking about extremely metal poor O stars.
All right. Thank you. And thank you to the organizers for putting together this great meeting and for having me here today. Okay, so yes, I'm going to tell you about some of my work on observations of very metal poor O stars. And I'd like to start by motivating the need to understand these stars in particular better. So early on in their evolution, the most massive stars appear as O spectral types and are capable of producing ionizing radiation. And at low metallicities, these are the stars that are driving the evolution of dwarf galaxies and also dominating the light and ionizing flux from galaxies at high redshift that we're now routinely observing with JWST. But for the purposes of this focus meeting, the most relevant aspects are that many of these O-type stars will eventually explode as supernovae. So if we hope to be able to link transients to the correct progenitors, and particularly the more exotic transients that we only see in very low metallicity galaxies, then we need to understand the physics and evolution of these low metallicity O stars. And this is also important for modeling, stellar feedback and nucleosynthesis across cosmic time. But below the 20% solar metallicity of the small Magellanic Cloud, we do not have spectroscopic observations of very many of these very low metallicity O stars. With the exception of a handful of stars that have been found in the Magellanic Bridge that we'll hear about from Elisa next, most of these stars can only be observed in much more distant galaxies that are at the edge of the local group. And so our observational sample is limited, and we do not have the empirical data necessary to test and calibrate massive star models in this very low metallicity regime. Okay. So this is the gap that I am seeking to fill with new observations. So this talk is going to focus on this sample of three very metal poor O stars that are found in 3 star-forming galaxies between 1 and 1.6 megaparsecs away. These span 3 to 14% solar metallicity in terms of their gas phase oxygen abundance. And our team observed these 3 stars with the Hubble Space Telescope's COST instrument and got these nice far UV spectra. The data are quite rich and contain a lot of photospheric features that encode a lot of information about the stars. But for this talk, we are just going to focus on a pair of metal resonance line doublets that are sensitive diagnostics of the mass loss rates that we've been hearing about all morning and were so nicely summarized by Andreas's review. So, right, the energetic radiation from these stars drives material away from the stellar surface. This is known and expected to be a metallicity dependent phenomenon, but as we've been hearing, they're very uncertain still, and that is particularly true in this very low metallicity regime. And again, the talks this morning have emphasized how important it is to get the mass loss rates correct for modeling stellar evolution. So from these COST data, we see just empirically that these are very weak stellar wind profiles, meaning these are not fully developed P Cygni profiles, right? So these stars have to have low mass loss rates. But to actually quantify that statement requires additional observations because, again, the far UV spectra are essential diagnostics of mass loss rates, especially at the lower rates that we expect for these low metallicity stars. But they are not sufficient because you cannot actually constrain some of the fundamental stellar properties from the UV alone to break degeneracies with the mass loss rates. So in a new paper just on the archive a couple of weeks ago, we present new optical spectroscopy of these 3 stars that we obtained with the Keck Cosmic Web Imager, or KCWI. This is an extremely blue sensitive integral field unit spectrograph mounted on the 10-meter Keck telescope. And that means that in each pixel of these white light images, we have a complete R of 4,000 optical spectrum. And each of these is showing a 16 by 20 arcsecond field in each of the host galaxies. And so we can extract the 1D spectrum of each star from these blue circles that I have indicated here. And the resultant spectra look beautiful and contain a suite of diagnostic lines that encode a couple of key stellar parameters that we really need to pin down. First is the surface gravity, log G, which comes from the Balmer line wings, and also the effective temperature, which for O-type stars, we get from the relative strengths of the helium-1 and helium-2 absorption features. And so with these new optical spectra in hand, we then did a quantitative analysis of the combined COS and KCWI observations. We fit new power stellar atmosphere models and tuned the parameters of those models to simultaneously match the full suite of features that we see in the optical and UV parts of the spectra. And then from those best models, we infer the fundamental stellar properties and also their wind properties. And so we can finally compare the mass loss rates of these stars to model expectations. Okay, so this figure is showing mass loss rate as a function of stellar luminosity. Our 3 stars are these colored points with the black error bars. And then for comparison, the colored lines and squares here show theoretical mass loss prescriptions at the same metallicities. And these color codings are the best fit iron abundance in our power models for each of the 3 stars. And so the takeaway from this figure is that we are seeing evidence for much lower mass loss rates at the very low end of this range of theoretical predictions, which again, we've been hearing all morning how there's all this debate in the literature over which mass loss prescription we should be using. And so I would say in this low luminosity and low metallicity regime, we are seeing the best agreement with the Bjorklund et al. Models. Okay, and again, we've been hearing from Emma and Olivier's talks about how important this is to consider in stellar evolution models. So we are seeing basically an order of magnitude lower mass loss rates than expected from this classic Vink et al. Prescription, which is typically adopted in grids of stellar evolution models that are used in applications like population synthesis. So this is really something to consider when developing new stellar evolution models. Okay, I want to end by briefly highlighting a surprising finding from this analysis, which is that the fundamental properties of the 2 stars in this sample below 10% solar metallicity do not match expectations from single star evolution models. And so specifically, we find higher surface gravities for these 2 stars than would be expected from their positions on the Hertzsprung-Russell diagram there. So they appear to have surface gravities more consistent with early main sequence dwarf stars. And this could be pointing to essentially incomplete physics in our stellar models at low metallicity. Or of course, we know that binaries are incredibly common at these high masses. And so a binary companion is a possibility, but even an equal mass binary does not fully alleviate this tension because it doesn't reduce the luminosity of the stars enough to bring them down to the main sequence. So another scenario could be that the stars have interacted with a companion in the past, but again, it's really difficult to identify an evolutionary scenario that simultaneously matches all of the available observational constraints that we have. So in some ways, these observations have posed new questions, and if you are interested in this, please come chat with me afterward. Okay, and then to conclude, I will leave you with the summary of my talk and close by advertising a new observing campaign that is expanding this analysis to a larger data set. So the TEMPOS program is a Cycle 31 Hubble Space Telescope Treasury program that is building a UV and optical spectroscopic atlas of nearly 30 of these low metallicity O stars in nearby dwarf galaxies. And it's really designed to be the most complete sampling of this O star parameter space that we can get in these galaxies, given the technological capabilities of our current observatories and our knowledge of confirmed O-type stars in these nearby dwarfs. So observations are underway, and stay tuned for results from TEMPOS coming in the future. Thank you.
Thank you. So do we have any questions? Okay, I've a quick question. You mentioned these weird ones that have higher mass than you would expect, or appear to have higher mass. You said they could be binaries. I mean, would we expect to see that in a spectra though? Do you just have a single shot of spectra, or do you have?
We do not have time series observations for most of the stars. We do not see evidence of changes in the radial velocities or the line profiles. I did try splitting our half night of observations into two, or checking individual exposures. There's really no evidence of that. And we also don't see absorption features that seem to require different effective temperatures, right? So it just doesn't seem like there are binaries there, and it's puzzling.
Thanks. We have 2 questions, I guess.
Thanks, Grace, for this lovely overview. I'm curious if you could also constrain the iron content, given that you have this iron forest. You mentioned that the iron content is known from the oxygen abundance, but could you also look at the iron explicitly?
Sure, yes. So we did our best to constrain the iron abundance. The uncertainties are, not great, but for the star with the lowest V sign I, we got reasonable, factor of 2 uncertainty on that. It seems like our best model, it favors SMC like iron abundance, but we cannot rule out, right, the gas phase oxygen abundance in that galaxy. So, the question is still open exactly what the iron abundances are, but yes, we can constrain at least from the iron forest.
Thank you very much for the excellent talk, very clear. If you were to make a guess as to what you will see from the 29 O stars in the TEMPOS survey, where do you think they would fit on that plot?
I mean, I don't want to go in with my mind already made up, of course, but I do think there is a very clear trend in the literature in recent years for this lower than expected mass loss rates at lower metallicities. So this is building on some work in the SMC that has also found a steeper metallicity dependence than would have been expected from the earlier generation of mass loss prescriptions. So I would expect to see more of that, but we'll see.
Thank you. Okay. So thanks, Grace, again. And our last talk of the session is Elisa Schoser, who's talking about Magellanic Bridge.
Yes. Hello, everyone. My name is Elisa Schoser, and I'm a PhD student in Andreas Sander's group. And today I would like to tell you about some new results about the spectroscopic analysis of metapoor massive stars in the Magellanic Bridge. As we heard already in all of the other talks before, the amount of mass loss is very important to study as it strongly influences the evolution and the fate of massive stars. And massive stars have a line-driven wind, and the main driver are metals. And this is why we also expect that there is a strong metallicity dependence. And this you can see here directly. You can see the mass loss rates as a function of metallicity. And for a constant luminosity, the mass loss rates increase. And on the right, I show you the results that just Grace showed you. So you can see the mass loss rates as a function of luminosity, and you can see with all of these lines and also this, the different prescriptions. And I want to highlight here again that there is a large spread from the theoretical predictions, and we need observations to find out which ones are the best. And one way is to go to these dwarf galaxies, but actually a postdoc in my group, Varsha Ramachandran, has found a different way of studying metapoor massive stars, which is in the Magellanic Bridge. she found that there are some O-type massive stars that we didn't expect in the beginning. And this is a unique environment because it's just very nearby. It's only 55 kiloparsecs away in comparison to these dwarf galaxies at 1 megaparsec or even further away. And it has an average metallicity of 1/10 solar. And so it is already half of the SMC, and so already much lower abundances are expected. And so it is a unique laboratory to study metal-poor massive stars. She found these O-type stars in just archival data of ESO, and we found that they are not really well studied. And she then studied these spectra from the VLT and with power that already Andreas talked about. This is a non-LTE one-dimensional model, a stellar atmosphere model. And she found that 2 of the O stars that she has found have very low abundances in CNO, silicon, and magnesium. But actually, there's one star that has a much larger abundance. And so this shows you already that this is a very inhomogeneous environment. And the first star also has a very large rotation rate in comparison to the other 2 stars. And we can study the abundances very well because all of these, the 2 other stars are much smaller rotating. And in comparison to the sample that Grace has just shown you, the stars that I'm looking at are much less massive. So this is also important to highlight. Here you can see another plot that Andreas showed already, and you can see the contribution of different elements and ions to the overall wind acceleration. And in the outer wind, there are many different elements contributing to it, but in the onset, the really important ion is iron. And so it is very difficult to fit the iron abundance, as we also heard already in the last talk, but because the stars that I'm now studying are very nearby, we can actually do that. And so here you can see the iron forest. So there are many different lines, and it is very difficult to then get the iron abundance just by eye fitting. And so I developed a Bayesian tool to just fit these iron lines. So I computed a grid with different iron metallicity, with different iron abundances, and then used interpolation techniques to predict the spectra in between, and then used an MCMC algorithm to fit the iron abundance. And I found for the 2 stars that also have smaller abundances in all of these other elements, they also have really low iron abundances. This one here has a 6.2% iron abundance, and then the other one has a 5.8% iron abundance. And here you can see, so now we have a full set of abundances, which is not really often possible for O-type stars that have low metallicity, but we can now plot all of these abundances against each other. And a typical way is this plot that you can see here on the left, where you plot the ratio of oxygen over iron, and then relative to the solar values. And then on the x-axis, you have the iron over hydrogen abundances. And in gray, you can see some lower mass stars from the Milky Way disk and the halo, and they follow a specific trend here. You can see a plateau and then a decreasing trend. And this is just because oxygen and iron are produced in different ways. So in the beginning, you have a lot of core collapse supernovae, which produces all of these alpha elements, as for example, oxygen. And then at a later time, you have these supernovae 1A that then produce all of these iron. And so you can see this plateau and then the decrease. And we haven't really studied this for more massive stars, but we find actually that one of the stars is following that trend and the other one is not. And then on the right, you can see the alpha enhancement of all of these alpha elements in comparison to iron. And you can see, especially in magnesium and silicon, that they show some signs of alpha enhancement, which is interesting result. And then I also studied the wind parameters, which we also heard already before is a bit difficult because they are not at this low metallicity. The wind features are non-existing or very, very small. And so you need to run a lot of different models. And there are many different parameters that can influence this. And I'm just showing here on the left side a model with a constant mass loss rate and different terminal velocities. And on the right side, I show at a constant terminal velocity with different mass loss rates. And you can see that they're changing the wind profile in a similar way. So this is already showing you that this is quite degenerate, and it is quite difficult to distinguish between both. And so this is still work in progress, and I can't really give you final results for the stars I'm studying, but I can tell you that the mass loss rates are very small, in the order of 10 to the minus 10 or 10 to the minus 9 solar masses per year. And then this gives me my summary. So Magellanic Bridge is able to produce O-type stars, which was very surprising result already in the beginning. We found 2 extremely metal-poor stars with only 6% solar metallicity and 1 LMC-like O-type star. One of the O-type stars shows signs of alpha enhancement. They all have weak winds. And I also want to advertise another campaign that is coming up. We have approved VLT observations we already have, and also approved cost observations of 21 stars that actually cover a much larger fraction, a spatial fraction on the sky and in the bridge. So the ones that I showed you before all lie here on this point, and all of the other ones now around. And so we will be able to map the ion abundances across the bridge and actually study the wind and the stellar parameters, and hopefully also some lower metallicity across this bridge. And so, yeah, stay tuned for that. Thank you.
Thank you. Do we have any questions, either online or in the audience?
Very nice talk. How do the stellar abundances compare to the nebular abundances in the Magellanic Bridge of nitrogen and oxygen, if there are some? Do they agree? They should, right?
Yes. Well, it is quite inhomogeneous. So we found already with these 3 stars that they're quite distinct, like that they're quite different to each other. But I think the lower metallicity ones maybe agree better. But there are some that have more enhanced carbon and oxygen. So it's quite difficult. They're quite different from each other and not all the same. So it seems to be quite inhomogeneous.
Any last questions? Okay, if not, let's thank Lisa again. And thank you to all the speakers, and we reconvene at 1:30.
Hello, everybody. My name is Fabian Schneider, and it is a great great pleasure today for me to talk to you about the pre-supernova evolution and final fates of binary stars. If you go out and you observe massive stars, you'll realize that most of them are in binary star systems or even higher order multiples. And that means that most of these objects are going to exchange mass with the continuous. And so they form and they explode in solar masses. This same rule, and in general, we can also predict very high.
Hello, Hanin. Could I try my slides?
Hello.
Hey.
Hello. What?
Hi.
Can you hear us?
Yes, I can hear you.
Someone speaking on Zoom? Someone speaking on Zoom? Okay, can you try your audio? Oh, right.
So currently there is like a background slide that is shared.
Sharing your screen?
Okay, let me try. Mm,
Okay, we see it.
Yeah, this works.
Yes, perfect.
Okay, and so if I put it like that, very good. Awesome.
Try
Okay.
to next slide just to see if
Oh,
it works.
Yeah,
Okay, great.
super. Okay. Okay, then I guess that works. I'm sorry that I didn't pre-record that. Didn't have the time.
No worries.
But-
Good that you.
I'll make sure to stay on time. I was thinking to aim for 17 minutes since the slot is 22. Does that make sense?
Yeah, well, you have 19 plus 3.
Okay, sure. I'll add the backup slide.
Mhm.
Super. Okay,
Okay.
well then I'm happy. Thank you so much.
See you again later.
Bye.
Check that. I will check my emails now.
So
Actually.
where is
Thank
their
you.
office? Where's their office? Is it like a finance? 1% up.
Okay. Think we are about ready to get started with the second session of today. And all I've got to say about this session is I hope you really like binaries, because we're going to be talking about those and basically nothing else. And to start off the session, we have Tomer Shenar from Tel Aviv talking about observational constraints on massive binaries. So go ahead.
Thank you very much. Hello, everybody. Good afternoon. Indeed, I'm Tomer Shana. I'm faculty at Tel Aviv University, and I'm going to give you really a tip of the iceberg introduction about the very big field of massive stars and binaries. So I hope we will cover most of the interesting things here. Okay, so in case you're not from the field, or you're maybe visiting from another field, or you're new to the field, you might not know this, but I think most of us here know that massive stars are typically in binary systems. Actually, we think that something like 100% of them are in binary systems. Not all of them will interact, but many of them will. So something like between 50 and 70%. That's what we're finding now. We're also going to see it during the talk. You see here a lot of different examples for how we find those binaries in different forms of interactions. So it's a very rich field that is really growing right now. So during this talk, we're going to take a tour through some of the main evolutionary phases of a binary as it evolves, starting from the pre-interaction phase, where we have two massive stars that have not yet interacted. This is a phase which we want to study if we want to probe the initial conditions with which massive stars start their lives. How many of them are in binaries? What are the orbital parameter distributions? Later, as the primary will evolve, it can feel its Roche lobe. The two stars can merge. We're not going to talk about mergers today. We are going to focus on the, let's say, the somewhat better understood phase, which is stable mass transfer, where one of the stars have lost mass, the other one has gained mass. And we're going to talk about these evolved phases. These are the phases that we want to compare our models to test our understanding of binary evolution. And for many of you guys working on supernovae, these are also your initial conditions, especially before one of the core collapse happens. So we're also not going to talk too much about the various techniques that we have to study a multiplicity. We can do that on different scales. As you can see here, today we're going to focus mostly on the regime of binary evolution. So this is the regime up to about a physical separation of about 10 AU. More distant? Closer or further away? Like this. like this. I feel like I need to fine tune my position. Okay, I'll try not to move too much. The physical, we're talking about. Can I use this one? Sorry for that. I like to move. So we're talking about the regime of binary evolution, which is physical separations of up to about 10 AU, corresponding to orbital periods of up to a few years. If we look at the corresponding observational techniques that we have to cover all these different scales, you can see that if we're talking about binary evolution, it's really spectroscopy, which kind of covers this regime most holistically, let's say. So it's kind of the bread and butter of most of the results that I will show you. This is not to say that photometry, interferometry, and high precision astrometry are not important, especially for some subpopulations. Another thing I want to highlight is that we're going to talk today a little bit about observed binary fractions and intrinsic ones. So when I say observed, I mean we had a certain study and people counted how many binaries there are and they report a certain observed fraction. To get to the intrinsic binary fraction, you need to do some kind of a bias correction. You often need to assume something about the underlying distribution of or population of stars. It's a bit more involved, but it's important that we compare apples to apples when we discuss these things. So I just wanted to introduce these terms. So we're going to kick off with the pre-interaction phase. We have two massive stars that have not yet interacted, potentially on their way of forming some gravitational wave merger. The majority of them won't do that, but some might. And this corresponds to OB-type stars. Yeah, massive stars on the main sequence. They're typically classified as OB-type stars. So let's see what we know about them. So OB-type stars have been spectroscopically monitored over the past decades in various regimes, both in clusters as well as in field stars, mostly in our galaxy, but also in the subsolar metallicity environment of the Large Magellanic Cloud, which is about a fifth of the solar metallicity. And the results are more or less consistent within these regimes. If we're talking about O-type stars, which are the more massive counterparts, they weigh at least 15 solar masses, the observed binary fractions range between 30 and 60%, but once one corrects for observational biases, the intrinsic binary fractions are somewhere between 50 and 70%. Since we're probing here the regime of binary evolution, this is kind of why we concluded the majority of massive stars will interact. For B-type stars, which are the early B-type stars, are the lower mass counterparts, let's say masses between 8 and 15 solar masses, the binary fractions tend to drop a little bit, but are still pretty high, somewhere between 40 and 60% for the intrinsic fractions. What we haven't really done so far systematically is to check whether this persists even at lower metallicities. And we've heard in many talks previously, we really care about knowing what's going on at low metallicity. Many of the phenomena and the transients that we observe are uniquely observed at low metallicity conditions. So we have heard of lower metallicities in previous talks, but what we're doing with this program is we're systematically probing massive stars in the small Magellanic Cloud, which probes a metallicity content of about a fifth solar. This is a new ESO large program called BLOOM, or Binarity at Low Metallicity, that I'm leading with Julia Bodenstein, and some other people in the room are also involved. We are collecting 25 epochs of spectroscopy over 2 years with an instrument called FLAMES for about 1,000 massive stars. This will result in a lot of science. We already have a characterization of the sample on a Hertzsprung-Russell diagram, so you can see it's a representative sample. So we didn't cherry pick the stars here, but it was kind of like blindly selected to be representative for the underlying massive star population. We have OB-type stars, P supergiants, and even yellow supergiants, and we're going to have binary statistics for them. I just want to share with you one result which we really submitted just a few weeks ago, which is the multiplicity of the O stars in the sample. And for the first time, we're kind of probing how the binary fraction may depend on metallicity, and does it even depend on metallicity? So first, I'm showing you results for low mass stars. So this is taken from a review by Offner et al. Note the low intrinsic binary fractions for low mass stars. And there is a clear trend with metallicity. We can see that the binary fraction increases as the metallicity drops. This has something probably to do with the formation process of binaries in the low mass regime. What do we observe now for the massive stars? We're not probing, unfortunately, this very rich scaling metallicity, but this is the Milky Way LMC and SMC dots. Basically, okay, you can fit some linear regression, you get a trend, but it's basically consistent with flat. It's consistently high. The bottom line is, first of all, we're finding a lot of binaries also in the SMC, something of the order of 70%, and we don't find a clear trend with metallicity. Another thing we really care about are the distributions over the orbital parameters, things like the orbital period and the mass ratio. How do they distribute in these populations? These are usually denoted as power laws, as written here with the pi and kappa indices. When one tries to derive these indices, again, you need to do some kind of a bias correction. I'm showing here one example from the VFTS survey in the Large Magellanic Cloud. One finds this exponent to be very close to 0 on log p, meaning that we have roughly the same number of binaries in bins between 1 and 10 days, 10 and 100 days, 100 and 1,000 days, and so on. In other words, binaries really like to be in shorter periods. This is why the majority of them interact. On the other hand, we can look at the Q, the mass ratio distribution. And this is a study where we really went deep, down to about 1/10 in terms of mass ratio. So it's really extreme, correcting for biases and doing a whole bunch of other stuff I won't talk about. We find it very close to be flat on Q. That means that if I have a massive star, say it weighs 20 solar masses, the probability for the companion to weigh 20 or 15 or 10 or 5 solar masses is the same. It's very different than the IMF. It also means that massive stars are very likely to have massive star companions. Will it persist at even lower metallicity is one of the things that we also want to probe with Bloom that I just told you about. So this was just a bit of the tip of the iceberg about the pre-interaction phase. Now we're entering the realm where one of the stars have filled its Roche lobe, donated mass to the companion, and we get something that is called a helium star, a strip star, Wolf-Rayet star. We're going to talk a little about those. And the mass accretor, I'm going to talk a little about later. Okay, so we have all these different names for stars that have lost their outer layers, but these are not just names, they're actually different objects. So this is a nice diagram taken from Ylva Göthberg's work. And you can see here the different spectral appearance of different types of stripped stars. Okay, so on the upper end here, at the luminous end, we have the Wolf-Rayet stars. Wolf-Rayets are, or classical Wolf-Rayets are stars that have lost their outer layers, but they are close enough to the Eddington limit such that they launch powerful winds, that give rise to these emission features. Okay, so if you don't have these emission features, it's not a Wolf-Rayet star. That's an important distinction because when we observe them, when we call something a Wolf-Rayet star, only when it shows these features, strong emission lines. If you don't have these features and it's a massive star, we generally call these objects stripped stars, lacking a better term, and we're going to hear a lot about those from Ylva in the next talk, I'm sure. In the low mass regime, they're called subdwarfs. Okay, I'm going to talk about Wolf-Rayet stars and let Ylva, I guess, cover the strip star domain. So the problem with Wolf-Rayet stars is that it's not clear that they're actually binary products. It's been known since the 70s that, at least in principle, Wolf-Rayet stars may originate in single stars. For example, if we take a 15 solar mass star in our galaxy, okay, it's probably going to end its life as a red supergiant, explode as a type 2 supernova. But as we climb up the mass ladder, eventually we think that some stars will be able to strip themselves off their outer layers and get into the classical Wolf-Rayet phase because they have such strong mass loss rates and such big cores. Where exactly this transition happens is not clear, okay? And it's super model dependent on our prescription. Some would say it maybe never happens, especially at low metallicity. But we more or less agree that probably at low metallicity, this transition happens at much higher masses because the mass loss rates decrease, as we've heard already many times. Even that is not 100% certain, but this is more or less the consensus right now. On the other hand, we have the idea of binary stripping, right? So we have a star that might want to become some red supergiant. We put a companion next to it, and instead it becomes a stripped star, which has these different flavors. If it's at the luminous end and it can drive powerful winds, it will look like a Wolf-Rayet star. So that's the so-called binary formation channel. And at least in principle, you would expect that this process is less dependent on metallicity. All you need to do is to strip the companion. And if you do that, you would get your strip star. And so you might naively expect that as we probe Wolf-Rayet populations at lower and lower metallicities, we would observe more and more of them in binaries. But that's not really what is being observed. So these are the observed binary fractions reported in different regions, from the Magellanic Clouds to supersolar environments in other galaxies, always somewhere around 30 to 40%. Is this surprising? So it's actually not surprising if you think about it carefully. And I'll try to explain very briefly why. These are observed populations. We've seen this also in Andreas's talk of Wolf-Rayet stars, WN stars specifically, in the Milky Way, the large and the small Magellanic Cloud. So this is solar metallicity, half solar, and about a fifth solar. And what you can see from these populations is that the Wolf-Rayet phenomenon kicks in at higher and higher luminosities. This makes sense because to look like a Wolf-Rayet star, you need to drive a strong wind. The winds of the stripped stars become weaker at low metallicity, and so you will need to get a higher mass stripped star if you want to get this Wolf-Rayet appearance. In other words, in a galaxy like the SMC, I would need to start with a much larger mass, something we estimate in this paper, something like 37 solar masses, if I even wish to get this Wolf-Rayet phenomenon. But these kinds of stars also get close, maybe, to where they can actually self-strip themselves. So it's a bit involved, but the bottom line is that at low metallicity, it doesn't matter how you strip your star, both of these channels are not that efficient, both binary as well as a single star channel. So it's not clear that there should be a trend with metallicity. But the more urgent problem is that we cannot explain the formation of the majority of these Wolf-Rayet stars. And this is just one example in the Large Magellanic Cloud. These are the observed positions of the Wolf-Rayet stars in the Large Magellanic Cloud. The majority of them are observed to be single. Evolution tracks really don't want to go there. So we want to put companions and get them all stripped by companions, but we don't observe these companions. We're really trying to look for these companions as best we can. So we just had a survey for the apparently single Wolf-Rayet stars in the Small Magellanic Cloud, not finding any companions with high resolution spectroscopy. Karan Zilva and his PhD tried to look again at the galactic Wolf-Rayet stars, not finding any new companions. And now we also had an interferometric survey of Wolf-Rayet stars in the galaxy and no really new companions found. So either we're still missing them somehow, or there is really some agent in the evolution models that we're missing that would make these stars strip themselves. As we've heard in previous talks, this is not so easy. Very briefly about, I want to talk about the mass accretors, just one slide. When stars accrete mass, they also accrete angular momentum. And it's, at least theoretically, you would expect them to rotate very quickly, very efficiently, reach to near critical rotation. When stars do that, they tend to develop decretion disks. They become kind of like ballerinas. And we observe emission features coming from these disks. And these kind of objects are called OE and BE stars. So unlike Wolf-Rayet stars, OE and BE stars, there is overwhelming evidence that they are predominantly the products of binary evolution. One way to see that is that every time we find a companion next to an OE or BE stars, it's a funny companion, like a helium star, a subdwarf, a neutron star. What we never observe, especially in the massive star regime, we never observe normal main sequence stars next to these stars. Yeah, so if they were like normal stars that have not undergone binary interaction, you might have expected to see some main sequence next to them. We don't see that. But ironically, we conclude that the majority are binary interaction products, but the majority, 91% of them, are observed to be single. Okay, so that's the unintuitive thing. What are these 90% systems? If they really have a binary origin, are they disrupted systems that have once had a neutron star companion maybe and got disrupted, or are we still missing their companions? This is still work that needs to be done. We don't have these constraints. I will finish off by touching upon very briefly this phase. I think that might interest some people here also, because we're talking about the phase after core collapse. Okay, so the star has undergone core collapse, and then we get a star plus black hole, star plus compact object binary. I'm going to focus on black holes. And I just want to address one question that I think interests many of us, which is, do stars explode when they collapse into black holes? We heard also yesterday, there's this idea of islands of explodability. So what do observations tell us? So the majority of black holes that we found in binaries come in this phase, right? They're called X-ray binaries, where the black hole accretes material from a nearby star. We know of about 50 black holes in this phase, and they are pretty easy to detect. They shout at us in X-rays, but they're actually only a minority of systems that will go through this phase. And because of the strong interaction, they are hard to interpret in terms of, it's hard to know how the black hole formed. Basically, they don't maintain the pristine conditions that existed when the black hole formed. What is much more helpful in this sense is finding black holes that don't strongly interact with their companions. There are so-called dormant black holes. They should be about 10,000 times more common than X-ray binaries, but we hardly found any of them. And this is simply because they don't shout at us in X-rays. Okay, so we need to be smart about how we find them. And typically we find them by seeing the other star moving around. We can do this either with Gaia, with high precision astrometry, or with spectroscopy. And indeed, over the past years, this field has been seeing kind of a renaissance. Most of the black holes that were found so far around low mass companions were found with Gaia. The last discovery was about 2 months ago for a 33 solar mass black hole in our own Milky Way. These objects are not super easy to interpret because they could have formed from dynamical captures. The other two systems that we know with dormant black holes have massive star companions, and they were found with spectroscopy. And at least one of them, VFTS 243, gives us pretty robust evidence that the black hole in the system formed without any explosion. Why? Because we see that the orbit is almost perfectly circular. Okay, if the orbit if there had been an explosion, we would have expected to see some eccentricity. So this is just a field that is really growing. In the coming years, we should have tens or maybe even hundreds of more such detections. I'm going to finish off very quickly by summarizing this pretty intense talk. First of all, I encourage you to check out this recent review by Marchant and Bodensteiner, which summarizes some of the things we talked about today. I touched upon the pre-interaction phase. We talked about the fact that the majority of stars will interact, that the distributions are flat on log P and Q, and that there is no evidence for metallicity dependence. For the post-interaction, we talked about the fact that about 50% of the Wolf-Rayet stars don't have companions, and that is still an open question, how to form them. Unlike the Wolf-Rayet stars, the OE and BE stars are very clearly binary interaction products, but we're still missing companions for the majority of them. And finally, we're starting to find those star plus black hole systems, which give us some first constraints on what happens in the core collapse process when they collapse into black holes. So with this, I will end, and I'm happy to take any questions.
All right, so questions.
Thanks for the great talk. So I'm curious about the Q distribution. You said it's consistent with flat. Down to what Q?
So in the study that we probed, down to 0.1. So yeah, 0.1.
Thanks.
Hi, about the last point. Actually, it is very interesting, but the Gaia sources seem to have quite large orbital separations, right? These are orbital periods of years, and the other sources you mentioned are very close. So how is it possible that the black hole is not accreting neither from the wind nor from the Roche-Loeb overflow?
Okay, so in the systems where the black hole is close, I wouldn't say it's not accreting. It's accreting. Kushik-Sen actually has some interesting work on this. It is accreting, but to launch powerful X-rays, you need to get an accretion disk. Okay, and they're far away enough such that the accretion disks do not form, and so they don't appear as X-ray binaries. The spherical accretion probably happens, but we're entering the domain of what is called advection dominated outflows, very low efficiencies. It's not clear how much, but they probably emit very, very little X-rays.
Okay, we can do one more question, if there is one.
Apart from the dependence on abundances, do you find any evidence on environmental effects? The reason I'm asking, I'm coming from the high redshift. You know, the very famous object there is GNZ11, where there's evidence for a hard radiation field and possibly anomalous abundances. And the suggestion, I wouldn't call it, well, it's a kind of suggestion only, is that these stars, these massive stars, form in very dense clusters, and therefore they merge. There's a higher fraction of binaries. You have stripping, and therefore you have a very hard radiation field. Do you see any evidence that there's a higher fraction of binaries in dense clusters as opposed to loose clusters in the field?
There is no evidence in the literature for that, as far as I'm aware. There is a dependency on the age, for example, on the age of a cluster. But that's very involved because as binaries evolve, you would expect them to be less and less detectable. That doesn't mean that they're not there. So it's an involved question. I can tell you that in the Small Magellanic Cloud, we have various fields that we are exploring various environments, but it's still too early to tell you if we see any dependency on the environment in this sense. But yeah, the environment could play a bigger role than metallicity in this sense.
All right, so let's thank Tomer again. And our next speaker is online. So, Ilva, are you there?
Yes, I'm here. Is it okay if I share the screen?
Yes. Right, so our next speaker is Eva Köttberg talking about strip envelope stars in binary systems. Go ahead.
Thank you so much, and thank you so much to the organizers for inviting me to speak. I'm sorry I cannot be there in person, but I've actually been a bit sick, so you're probably better off without me. My name is Ylva Göthberg, and I work at the Institute of Science and Technology, Austria. And for this talk, I borrowed this background slide that we made for a recent workshop in the Lawrence Center, showing you how interaction binaries we are seeing at the top of an iceberg, but maybe there is a lot of interesting things going on in the rest of the iceberg there. So today I will try to give you a little bit of an overview for envelope strip stars in binary systems, as Tomer also mentioned too. So it's great because today we had a few talks that relate to this topic, and also yesterday, so I already gotten some help. So as an outline, I was thinking we can start with describing a little bit what is a strip star, and talk about what I think that we could define that as at this point, or just for today. Then going into what is the importance of these strip stars. And lastly, I would like to give a little bit of a view of the observational status of these objects. So to begin with, what is a strip star? In this work from Uxana and collaborators in 2012, they identified also this data point that Tomer just showed us, that most massive stars are in binaries, and in fact, a third of them are expected to go through envelope stripping. So what is envelope stripping? I can usually think of 3 different channels to strip off the envelope in the binary, 2 of which are mass transfer, either initiated on the main sequence or after the main sequence. And then we also have a successful common envelope ejection. This should lead to the helium core being exposed, and that is what here is referred to as the stripped star. How you create this, for example, through mass transfer, we can look at a standard HR diagram here with the surface temperature going in the reverse direction and luminosity on the y-axis. And I'm going to show you the evolution of a 12 solar mass star that has an orbit with a binary companion of 20 days. It starts off there fusing hydrogen to helium in the center during the main sequence, where it evolves like this. After the main sequence, it starts this mass transfer phase when it tries to expand a lot to become a red supergiant. And most of this envelope is now stripped off, but you're left with a tiny little bit of this helium in the enriched layer above that helium core. And that remaining core is now contracting towards this helium core burning phase, which is located at really high temperatures. And in the case of this 12 solar mass star, it created something like a 4 solar mass strip star. Eventually, when it exhausted the helium in the center, this star expands again until it reaches core collapse and would then explode as a hydrogen poor supernova type 1 BC or so. This changes completely the evolutionary scenario for these 12 solar mass stars, which if it was a single star would have reached very low temperatures and exploded like a hydrogen-rich supernova. So this type of envelope stripping really changes the stellar evolution. Now, how common are these stripped stars? This is a recent study that we're about to submit together with a student I've been working with, Beryl Hovis Afflerbach. She's now a PhD student at the Northwestern University in Chicago. So what Beryl did was to run a binary population synthesis code that is based off of detailed binary evolution models, such as the one I just showed you, and to use grids of such models for different metallicities to predict how many stripped stars we would expect in a constant star formation population of 1 solar mass per year. And here we can see a rather easy diagram, once you're familiar with it. It shows it's a reverse cumulative number distribution of stripped stars. So here we have the stripped star mass in the reverse direction, and it works like this. For example, if we're interested in the stripped stars that are more massive than 2.6 solar masses, which we think is the boundary between white dwarf and neutron star formation, then we're going to follow the line over there, and we find that this should be several thousands of stripped stars of that mass available independently on the metallicity of the population. However, you can see a difference with metallicity at the higher masses, and especially at low metallicity. In fact, the binary evolution is not so efficient at forming massive stripped stars. So it is not just the effect that Tomer just mentioned, but actually they don't reach binary stripping because the star expands at a later stage, or as has been discussed in Jakob Klensky's paper from 2022, which here shows you what happens to this SMC metallicity star that enters a mass transfer phase, but just continues transferring mass during that stage, since the star never expands to try to become a red supergiant. So such partial stripping or unfinished stripping prevents the creation of hot stripped stars that can populate this high mass regime, which I think is rather interesting. There is also another type of stripped star, or if we look at the stripped star stellar evolution, there is a different type of evolutionary stage. And this is a work that I was not involved in, but I like to show the Basish work, since he is also going to join us at the ISTA. So what they show in this paper is here for two different metallicities, one higher metallicity and one lower metallicity, the evolutionary stages of a 16 solar mass star that creates something like a 5-ish solar mass stripped star after the mass transfer stage. And what you can see here is the hot stripped star phase, which lasts about 90% of the stripped star time. But there is also this cooler and faster puffed up phase that takes about 10% of the time. Now, the Basish paper is going much more in detail, so I definitely recommend you looking into that, because it's interesting that it in fact is not faster than 10%, but the fact that it is 10% makes it actually perhaps easier to find such cool, puffed up, bloated stripped stars, since they are significantly brighter in the optical bands during that regime. And that is also something I will get into a little bit later. So now moving on to the importance of the stripped stars. I think this slide, you probably are already convinced, so I'll go quickly. This is the spectral energy distribution from the 1b supernova IPTF 13 BVN, which was detected through pre-explosion images. And here, Jan Eldridge put several matching progenitor SEVs to match this a helium giant of 3 to 7 solar masses, which they found are located somewhere there. And here you can see overlaid with several BPAS models. However, such helium giants that are sufficiently massive to reach core collapse remain unobserved. And I would say it would be really interesting if we could observe them. For example, there has been several predictions made by Kim and collaborators, and also Jung and collaborators, for how such helium giants should look like. So this would be really interesting, so that we can learn better about, for example, late stage mass loss rates, and what type of star it is that is actually exploding, how we should change our stellar evolution models. When it comes to the entirely stripped supernovae, the 1C, this becomes challenging. So this plot is from Thomas Tauris in 2015, where he shows the initial mass of a helium star and the orbital period in the different lines here, so that this helium star would then interact with its companion and lose material until it is no longer a helium star, but instead a naked carbon-oxygen core that can eventually explode. And if you look closely, you can see that this is somewhat mass dependent, but you really, really need a very short orbital period for such a system for sufficient amount of material to be lost, so that the star can become a 1C supernova, helium-free star. These orbital periods required here are just a few hours, which is not going to be possible unless you have a compact companion. I think we have found an example that could potentially be a progenitor of this. So I'm working together with a graduate student, U Toronto, Bethany Ludwig, and her advisor, Maria Drought. And this is an example of a radial velocity fit that we did to a 3 to 5 solar mass strip star. We don't know exactly what is the mass of the star, since we cannot see the companion, but the companion has something like 1 solar mass probably, and the orbit is about 4 hours. So depending a little bit on the mass, probably we are either in the 1C or 1BC regime there, but we're working on the modeling at the moment. Then strip stars are, of course, also progenitors of gravitational waves. Tomer showed you this diagram just previously, which is showing you the evolution towards a gravitational wave merger. When you create a strip star, through mass transfer, it explodes or goes into a compact object, which later can evolve and bring the stars close together. And eventually, those two compact objects can merge in a gravitational wave event. So in fact, it's interesting to note that you don't just need one strip star to create a gravitational wave merger in the standard isolated binary evolution channel, but in fact, both objects need to be stripped. In this particular study that I'm going to show you, we were working here on the strip stars in this phase, because you can calculate what's the gravitational wave frequency, and down there we have the LIGO frequency of order of seconds, but up here it's the order of hours, where LISA should become available, and so that we can actually observe such gravitational wave sources that also are bright in the visible electromagnetic regime. And I made a small population study of that in 2020, where we found that it's possible that in the Milky Way we have something like a handful of such objects that are sufficiently massive so that we can actually observe them here in a sufficient gravitational wave strain, but they would need to be rather nearby, which is also exciting. Strip stars can also be interesting in terms of ionizing radiation, since they are for most of their time in this hot helium core burning stage, where they then emit a large amount of ionizing radiation. Here is a study that we did where we compared with Starburst 99, the hydrogen ionizing emission shown on the y-axis, and the time after Starburst on the x-axis. And you can see that first in green, the most massive stars in the system, they emit a lot of ionizing radiation at high rate, but stripped stars that come from somewhat lower masses, they dominate the ionizing emission at later times. This can also change entirely how the spectral energy distribution looks like. So here, after about 20 million years, you can see that it significantly boosts the ionizing regime. But if you look in the ultraviolet, you're not going to see any contribution from these strip stars directly. So perhaps instead you would need to look for nebular emission, ionization of surrounding gas, etc. And this is something that I think that we see in this star that Peter Senchina and Maud Gull have recently detected. This is a star in the extremely low metallicity galaxy Leo A, 4% solar metallicity. And after analysis here with the CMF-GEN spectral modeling code, we can note that this star is leftwards, bluewards of the 0H main sequence. And it also matches this evolutionary tracks for extremely low metallicity stripped stars. But it also has this puzzling slow outflow with emission lines in helium. So hopefully we can use that to better understand the ionizing hardness of this object. Moving on to the observational status, and here I'm probably going to have to skip some slide. This is from the review of Pablo Marchant and Julia Bodensteiner, where they show here you have the 0H main sequence and some evolutionary tracks of stars that move through the mass transfer phase here shown in yellow. And over there is the helium main sequence, or the helium core burning stage. And what the data points is showing you is the detected stripped stars. So we can see here that there is a group that are cooler than the 0H main sequence. And then there is a group that is hotter than the 0H main sequence. So we can prepare this divide. And this cooler stripped stars is an interesting group. They are often identified as narrow-lined O or B-type stars that orbit a BE-type star, this rapidly rotating star that Homer mentioned. They tend to have high luminosity to mass ratio, so they have low surface gravity and are fluffy, and they have nitrogen enrichment often, and sometimes also helium enrichment. Here is an example from Jaime Villaseñor in 2023, where he separated this binary VFTS 291 into about the 2 solar mass stripped star with a 10-15 solar mass E-type companion. And it is really quite striking how much faster this low mass companion moves around the BE-type star. So it is clear that this is a much lower mass companion. The prediction from the bathysian, the Jakob, was that this could actually be a relatively common evolutionary state, a common object, given how many binaries we have. So we just need to look a little bit more for these bloated objects. Maybe there is many more out there. There is also several recent surveys for more hot stripped stars. This is some that me and Maria Draute led and found objects in the Magellanic Clouds. They tend to have high effective temperatures, surface gravity, and surface helium and nitrogen enrichment. The subdwarfs have been known for some time, but I want to point out that we have the subdwarf plus BE star systems that have recently grown in sample size. And these spectra that I show here on the right is more intermediate mass, where the masses are more in between 2 and 8 solar masses or something like that. So we fit those spectra. Here is an example, our star number 6 in the LMC, and which shows a set of different spectral lines to fit with CMF-gen models and could identify stellar properties for several of these objects. And I want to point out a few things. First, we think that there's masses that are sufficiently massive to reach core collapse. So there should be supernova progenitors here, although they are before the helium giant stage. And something worth noting is that there are both hydrogen-poor and hydrogen-free stars. So that is not something that we entirely understand yet, but it's interesting in terms of the supernova progenitor physics. I think I will skip the mass loss rates. You can ask me about that. Lastly, I think it's interesting to think about the parameter space distribution of stripped stars. If we imagine here that this is the initial mass of the most massive star in the system on the x-axis and the initial mass of the least massive star in the system on the y-axis, and here we have some distribution of binaries before interaction. I have removed this part because the secondary is more massive, and this part is also the part where that Tomer mentioned that has a mass ratio less than 0.1. So for the post-interaction system, we expect that this diagram has a bit of structure, that this could actually be quite informative to map out. For example, these up here probably have conservative mass transfer. So if we can measure the upper limit, that's probably the maximum mass ratio that you can get. That would be interesting to figure out what is this, so that we can figure out how much material can actually be accreted. There could be a gap in between these two populations, depending on whether you can actually have intermediate mass transfer efficiencies. There could also be a separation between non-conservative mass transfer and this common envelope ejection here, since this is related to also to mass ratios. And that is something that graduate student Alex Laroche at UToronto, Toronto, together with me and Maria Drought, also is working on, where he has started to place some double-line spectroscopic binaries in this parameter regime very close to the boundary between stable mass transfer and common envelope ejection. So with that, some future directions that it would be really interesting for better understanding these trip stars, in my opinion, could be to look for these helium stars that at low metallicity, try to find these pre-supernova helium giants, and the wind driving. I wanted to say that I think it's really important, but I attended Andreas' talk, so I think he was quite exhaustive. And of course, we don't have any intermediate mass trip stars in the galaxy, maybe just HT 45166. And it would be also very fun to try and fill out that parameter space. So with that, thank you so much for your attention, and I'll be happy to take any questions.
Right, so we got time for a couple of questions. Anything online, perhaps?
Hey, Ilva, thanks for the talk. Question about those inflating strip stars before they might produce these strip supernovae. What dominates the place where they stop inflating? Is it mostly the companions? And if so, like, would most of them look like blue supergiants or yellow supergiants? Or
this is a good question. Thank you, Tomer. So it depends on how much hydrogen is left. If you don't have hydrogen, it is actually the structure of the star that sets that, mostly the mass. So the lower mass ones, about 3 solar masses or so, they expand quite a lot, could reach a second stage of mass transfer. The more massive ones, they don't inflate very much. But if they have a little bit of hydrogen, what is dominating their location is the companion star. And they are expected to explode during a second mass transfer phase.
Anyone else?
Hi, Eva. Andreas here. Very nice talk. You showed this simulation from your student with the strip star versus metallicity masses. I was wondering, how high did the models go there? Because you were going all the way up to like 50 solar mass strip stars.
Well noted. Yes, that's a trick, a little ugly trick that we did, because indeed those underlying binary evolution models only reach like strip star masses of 8 solar masses or something like that. So what we did for the more massive ones was to use single stellar evolution tracks and map only the mass of the core and use that as the strip star mass. So for those stars, we don't have estimates for their properties, but we have a mass estimate, and that is simply just set by the core mass.
All right, so let's thank Ilva again. And let's move on to the next talk, which is a pre-recorded talk, I think, by Fabian Schneider from Heidelberg, who is also on Zoom to answer questions.
Yes, I'm here.
So are we getting the video up? Okay. Bit of a technical difficulty, I guess. Okay, should we switch perhaps? Okay, should be coming up. Right?
Hello, everybody. My name is Fabian Schneider, and it is a great pleasure today for me to talk to you about the pre-supernova evolution and final fates of binary stars. If you go out and you observe massive stars, you will realize that most of them are in binary star systems or even higher order multiples. And that means that most of these objects are going to exchange mass with a companion during their lifetime. This mass exchange itself can now take on different forms. For example, stars might simply merge altogether. Or one of the components here, for example, is being stripped off its hydrogen-rich envelope, and then this is being transferred onto a companion, which is then an accretor of such binary mass transfer. And because most stars do that, it means that most of the supernovae that you observe in the universe, they are actually from binary products. A prime example might be supernova 1987A. So today I would like to discuss with you our stellar modeling that we have done on this. And to that end, we have evolved single stars. I'm just showing one of such an exemplary track here in the Hertzsprung-Russell diagram. And we have evolved these models all the way up to core collapse here as a red supergiant. And then we have analyzed the core collapse using the neutrino-driven parametric supernova code by Bernhard Müller and colleagues. And then to mimic binary star evolution, we have considered different evolutionary stages on the main sequence, in the post-main sequence phase, before core helium burning, and also after core helium burning. And in these evolutionary phases, we have removed the hydrogen-rich envelope to mimic binary mass stripping. And we have also accreted mass to mimic mass accretion and also stellar merging. Okay, so let's have a look first at single stars. And it is well known that if you look into the compactness parameter, for example, of single stars, and the compactness parameter is just the mass divided by the radius at that mass coordinate in the interior. And if you look at this compactness parameter, for example, as a function of carbon-oxygen core mass, but I could have also plotted initial mass here, then it is well known that you find a non-monotonic function at core collapse. And this non-monotonic function has quite some interesting consequences. And the compactness parameter itself is particularly being used to judge the explodability of such stellar models. If you have, for example, a high compactness beyond some threshold, then maybe the star is more prone to collapsing into a black hole, whereas if you have low compactness, then maybe the star rather explodes and forms a neutron star. And so in that regard, we find high compactness in our models at carbon-oxygen core masses of about 7 to 8 solar masses, and also beyond about 13 solar masses. This landscape is something that we finally have managed to understand. And if you're interested in more details, I invite you to have a look into the upcoming paper by my postdoc, Eva Laplace. This landscape is also very insensitive actually to changes in physics. So here I've reduced the metallicity by about a factor of 10, but we've also played with convective boundary mixing and other physics. And this landscape qualitatively is always going to be the same. Even in binary split stars that I'm showing now here in red, the landscape does not really look dramatically different. There's going to be a systematic shift, but qualitatively, the landscape looks the same. And this would also be true for accretors and also stellar mergers that I'm not now going to show to you here. So if we then explode or let these stars collapse and look into what the compact object remnant that we get. And this is a picture. In blue, our single stars. In red, this is our binary, stripped binary stars. And you'll first of all notice that there are islands here of black hole formation as a function of initial mass. And these correspond to the compactness peaks that I just described earlier to you. Also, a big difference is being found for neutron star formation. In single stars, we form neutron stars for initial masses of less than 35 solar masses. And in binary stripped stars, you would form neutron stars all the way up to initial mass of 70 solar masses. It's a huge difference. You also find a neutron star black hole mass gap from our models at the moment at a mass range between 2 and 9 solar masses. And the width here in our models is controlled by the amount of supernova fallback and or also partial mass ejection in failed supernovae. There's none of that actually considered here. That's why this gap is relatively big. Another interesting factor is to look into the maximum black hole mass that we get from binary stripped stars. This is at about 20 solar masses at galactic metallicity. And this seems to be in agreement with the maximum black hole mass so far found in Cygnus X1. If you now look into binary stripped stars as a stellar population, what we have found is that we have on average higher explosion energies, larger nickel kicks, neutron star kicks, also larger nickel yields, and we would form fewer black holes in comparison to a very popular prescription used in population synthesis codes from Fryer and colleagues from 2012. Maybe one of the most exciting results is that we found is if you look into the black hole mass distribution of stripped stars, and we find this black hole mass distribution to be bimodal, and it's bimodal with the same pretty much black hole masses, also at a much lower metallicity. And this has led us to think that there are characteristic black hole masses of about 9 and 16 solar masses. And if that is true, they should of course also leave their imprints in observations. And this might actually have been observed today in gravitational wave data from from mergers of binary black holes, where you find exactly an overabundance here. The chirp mass distribution, it is at about 8 solar masses corresponding to this compactness peak black holes, and also then at higher chirp masses that might correspond to this high mass component of the black hole mass distribution. So this is very exciting to follow up also in the future. I'm going to change gear a little bit, talk now about accretors and stellar mergers. And first of all, I'm going to show to you some results here. What happens if you accrete mass onto a 13 solar mass star while it's still on the main sequence? Now, what you're going to observe is the star accretes mass, it rejuvenates, and then just evolves as a single star. Here explodes also as a red supergiant, for example. But however, if you do the same mass accretion, but only at a later evolutionary phase, namely after the main sequence, then you can turn the star into a blue supergiant that lives its rest of its life here doing core helium burning in the blue part, and also explodes as a blue supergiant instead of a red supergiant. Okay, let's talk about now the death zones in the Hertzsprung-Russell diagram. So this is where our single star models would end their life and collapse. And so they form a band here. And this band is pretty much reproduced also by the accretors and mergers that evolve into red supergiants. But on top of this band, you also get contributions from our mergers and accretors from blue supergiants, but also from stars that populate this region of classical, where usually classical luminous blue variables would live. We can also categorize the entire region here now according to maybe the appearance as light curve. So this would be a region here of type 2p plateau supernovae from red supergiants. This blue part might be a region where the supernova light curves look a little bit more like 87A. And we hypothesize that if stars explode in this LBV regime, then maybe the supernova type that you observe would be more of an interacting type 2n supernova, or maybe even a superluminous supernova. Now, interestingly enough, because we have this band here on the red supergiant branch, and because red supergiants at the core collapse stage follow a tight carbon-oxygen core mass luminosity relation, and because our accretors and the single stars all show the same compactness peak at about a carbon-oxygen core mass of 7 to 8, they also predict that all of the models here form black holes in this part of the Hertzsprung-Russell. And it's interesting that exactly at this luminosity, there was a star in 2009, a red supergiant, that has just disappeared and has been hypothesized to have collapsed into a black hole. So if true, this would of course be a nice confirmation maybe of our ideas that I've presented here. Now, onto another different topic. If you consider these stars here in the upper part of the Hertzsprung-Russell diagram, they might lose, of course, a large fraction of their mass by enhanced winds as luminous blue variables. And I've marked these objects now with white crosses. So these are stars that have spent more than 10 to the 4 years in this regime. And so maybe they will have actually lost almost the entire hydrogen-rich envelope, and then they would no longer explode here, but maybe as type 1bc supernovae. But there are still some objects left that have spent their most of the time as blue supergiants and thereby avoided the strong wind mass loss as a red supergiant, and they explode in this part of the Hertzsprung-Russell diagram or collapse into black holes. And interestingly enough, then we can predict, or we can form maybe black holes of up to 50 solar masses from such blue supergiants, or also supernova ejecta. We get supernova ejecta of up to 40 solar masses from stars exploding or collapsing in this part of the Hertzsprung-Russell diagram. Okay, so that leads me to my summary. So as I discussed today, I've made the point that most massive stars are sitting in or living in binary star systems. And that means if you observe supernovae, then you have a very high chance that whatever supernova you observe is in fact from a binary product and no longer from a genuine single star. I've motivated that in all of these objects, we find a non-monotonic landscape of compactness with the carbon-oxygen core mass. And in particular, we find high compactness at some characteristic core masses, carbon-oxygen core mass of 7 to 8 and maybe larger than 13 solar masses. This same feature is being observed in binary strip stars and accretus. In binary strip stars, this compactness landscape means that there are characteristic black hole masses at about 9 and 16 solar masses across a large range of metallicity, and also that the black hole mass distribution is going to be bimodal. For the accretus, we find that this compactness peaks gives rise to a region in the Hertzsprung-Russell diagram where stars are expected to collapse as red supergiants into black hole. And in general, we can also predict very high black hole masses and also supernova ejecta from our stars here at galactic metallicity. Thank you very much for your attention, and I'm happy to take further questions.
All right, questions for Fabian?
Hi, Fabian. Morgan Fraser. Just wondering, for the stars that explode as blue supergiants, the observed fraction of 87 A-like events is relatively low. It's probably on the order of a few percent of core collapse. And I guess some of them also seem to be quite, there's at least a handful, like 2009 AE, that are quite low energy and probably low progenitor mass. So I wonder, do you have any comments on the rates of these events and whether you can also get fainter, lower mass blue supergiant explosions?
Yeah, fantastic question, Morgan. So in general, okay, so what do you need to produce a blue supergiant? And that is going to set your rates. So you need to have a post main sequence plus main sequence star merging that limits your parameter space already a little bit. So that limits you maybe to something, let's say, some 30% of a massive star population that would do that also. And then in this merging, you need to accrete, or you need to retain enough mass in your star so that it can become a blue supergiant. Why is that? You need a specific core envelope structure to make a long-lived blue supergiant. And this will not be satisfied in actually most of these post-main sequence mergers. It is still unsure or unclear actually how much mass kind of you need to retain here. And that's going to be another diminishing factor in the rates. And if you take both of them then into account, I think one could easily make the scenario actually work with the rates of 87A like like supernova. Then on the extremely low energy events that you have in this regime. So what we have, I mean, we have tried to stay away a little bit in our studies from this low energy explosion energy regime because of numerical computation difficulties. So if you go into low ion core mass supernova, you need to take certain precautions in this entire business. And technically also what you can do is you can have a core of a star that maybe undergoes an electron capture supernova, but still turn that star into a blue supergiant and explode. And then my suspicion would be that you might actually get some of these events and objects that you were mentioning.
Okay, I think as we're a bit behind schedule that we need to move on. So the next, oh yeah, let's. And the next speaker is Mar Carretero Castrillo from Barcelona. Yes, yes, you can take. And her talk is about the runaway stars in specific.
Sorry, Where can I change the slides? Okay. First, thanks to the organizers for giving me the opportunity to present here. I am very grateful. I am Marc Carretero Castrillo, PhD student at the University of Barcelona, and this talk is really for runaway star lovers. I will talk about runaway stars and about the physical mechanisms that originate them. So first, runaway stars are those stars that have a high velocity with respect to their environment. There are several works about runaway searches in the literature that found a significant fraction of O and B type stars being runaways. However, there is a significant scatter among these results that comes from a diversity in the input data and in the method used. So we need a new work using the last release of the Gaia data and a more homogeneous method. And this is what we did. We searched for runaway O and B stars in our galaxy using Gaia 3 data. As for the runaway origin, there are two physical scenarios that originate them. One is the binary supernova ejection, when the runaway velocity is acquired after the supernova explosion of the most evolved star in a binary system. And the other is the dynamical ejection scenario, where the runaway velocity is acquired after 3 or more body interaction in the core of a dense cluster. So both scenarios can generate either isolated runaway stars or runaway binary systems. But the binary supernova scenario in particular can generate runaway binaries with compact objects, a black hole or a neutron star. However, the relative contribution of both scenarios are still poorly understood. So to find the runaways, we first use the GOES and the BESS catalogs of O and B type stars that we cross-match with Gaia DR3 data. We apply some quality cuts and we end up with a catalog that we call the GOES Gaia DR3 catalog with 417 O stars and the BESS Gaia DR3 catalog with 1,335 stars. After this, we compute the velocities of these stars, and for this, we use a two-dimensional velocity system because Gaia does not provide enough radial velocities for massive stars. And this two-dimensional system is composed of the velocity tangential to the galactic plane and the velocity perpendicular to this plane. And once we have the velocities, we need to find the runaways. And for this, we define a runaway criterion based on how significant is the 2D velocity of these stars. With respect to the mean galactic rotation, and to do this, we define this E parameter that basically it takes into account the velocity distribution of the stars and the individual errors of each star, and it's normalized to 3 sigma. So that means that all the stars that have a E parameter E value greater than 1 will be classified as runaways. So yeah, all the methodologies explained in detail in the paper, but here I just review the main results. These are the two-dimensional velocity plots with the O runaways in blue and the B runaways in red, while the stars that we classify as field stars are in black. So we found in total 175 runaway stars, being half of them new discoveries. And we also found velocities of the runaways that reach up to 200 kilometers per second, being the O runaways with the higher velocities. And finally, we also found some non-high mass X-ray binaries, these binaries with compact objects, among the O runaways and the B runaways. And these systems are particularly interesting because they can emit up to very high energy gamma rays, among other many things. So as these are the projections in galactic coordinates with the distinction between the field stars and the runaways. And yeah, we know that during the formation as runaways, these stars have been expelled from their birthplaces. So this is exactly what we found when looking to the galactic latitude and the galactic coordinates, because runaways show a dispersion of 2 to 6 times greater than that of the field stars. If we move now to the study as a function of the spectral type, we found that the runaway percentage decreases as we move to later spectral types. Going to the literature, there are works that claim that the binary supernova ejection results in a slower ejection of less massive stars, while the dynamical ejections results in faster ejection of more massive stars. According to this, O type stars or runaways should be mainly produced by dynamical ejections, while B type by binary supernova explosions. And yeah, Torigo and collaborators, they they look for runaway stars in the small Magellanic Cloud using 2D velocities of Gaia DR2, and they found that the DES scenario dominates over a factor of 2 to 3 over the binary supernova 1. However, some collaborators they use 1D velocities in a cluster of the LMC, and they found the opposite, that the binary supernova ejections dominates this runaway star population. We found a factor of 5 within the percentage of O and B type stars, and this reinforces the dominance of the dynamical ejections. On the other hand, we have that stars with a projected rotational velocity greater than 200 kilometers per second, they are considered as fast rotators. And as we saw in the other talks, fast rotation is a clear signature of post-binary interaction products. So this is the diagram that some collaborators obtained, and here we have in the y-axis the projected rotational velocity, and in the x-axis the line of sight velocity. So yeah, there is a lot of information in this figure, but I want us to keep in mind that as we move forward in the x-axis, we find fast-moving runaways, and if we go up, we find fast-rotating runaways. So they found this, well, in the x-axis at 60 kilometers per second, we have the transition between the slow and the fast runaways, while in the y-axis at 200 kilometers per second, we found the transition between slow rotating and fast rotating runaways. So they found then these 4 regions where there is a clear avoidance regions where there are no fast rotating and fast moving runaways. But the most important result that they found is that they distinguish between these 2 populations. Population fast rotating but slow moving group, that is this one red here, in red here, and another population of a slow rotating but fast moving group that is related with dynamical ejections, and is the other in blue. We compute a similar plot. We found, but our sample is much larger. We also found this avoidance region. So in general, there are no fast-moving, fast-rotating runaways. We found the most important result for us is that we found that most of our slow runaways are also slow rotators. So this is in contrast with some results, and this indicates that most of our runaways are coming from dynamical ejections. Also, the walkaways, there seems to have no fast rotation. And yeah, comparing both samples, our is much larger. We are using 2D velocities, and we are working in the whole Milky Way. So coming back to the title of my presentation, are runaway stars produced by supernova explosion or by dynamical ejections? It's not really easy to answer this question, and there are many factors coming into play here. So our data shows that not theory, that there are no fast rotator walkaway stars. Most of our runaways are slow rotators, and that we have found a factor of 5 between the O and the B type stars. And all this indicates that the dynamical ejections dominates the massive runaway star population in our galaxy. So I will leave you with my conclusion here. As work in progress, I want to mention that now we are computing multi-wavelength studies and binary searches of this sample of runaways, because in this way we can unveil a population of high energy binary system hosting compact objects. And just I want to share a bit of my future plans, because I am finishing my PhD in about 1 year, so I'm starting to look for opportunities to continue my research. I have worked with these topics, and if you are aware of something, I will be very happy to talk. Thank you.
Do we have any questions, Omar?
Thank you for your talk. Could you tell anything about possible dependence of the runaway velocity vector and axis of rotation?
What do you mean with the axis of rotation?
I mean that the star, when it rotates, it has axis, and we have velocity vector. Are they coincide or perpendicular, or angle is can be of any value?
I am not aware of this. We can comment later on this. Sorry.
Another quick question, maybe?
Hey, thanks for the nice talk. I was wondering if you compared quantitatively your results with predictions both from the supernova ejections as well as from dynamicals? I mean, there should be some predicted distributions for these velocities. Have you done any sort of quantitative comparison with models in this sense?
Not, we are just working with the observational data because the Gaia data is now what is coming now, but we are starting to look into the models and the predictions, and this agrees with that. Yeah, binary supernova ejections usually have not that large velocity, so we expect that our B-type stars, B runaways, are coming from this, while the others maybe from this, but it's something to have a look on that, yeah.
All right, let's thank Mar again. And next up, we have Abigail Frost from ESO, talking about a nebula around a binary star.
Okay, hi everyone. Thank you very much to the organisers for giving me the opportunity to present this project today. I'm currently based at ESO, my name's Abby, but this is a project that I did with collaborators at KU Leuven whilst doing a project there. And I want to talk about how interactions can fundamentally change the properties of the stars in the system, and particularly inducing magnetism in an O-type star. So this is the system that we were looking at. It's called HG 148937, and it's a magnetic massive binary system. It was classified as a sort of OF P system due to the appearance of strong C3 and N3 lines, which we now associate this kind of class with magnetism in massive stars. It's a rare class. There's only a handful of examples of these objects. A magnetic field was measured directly towards the system with strength of 1020 Gauss by Greg Wade in 2012. And one thing that makes this system particularly weird, oops, that's the wrong button, makes the system particularly weird is this beautiful nebulae surrounding the system, which makes it very rare amongst not just O-type stars, but magnetic O-type stars. The system, as I said, is a binary system. It was the two stars were confirmed through an interferometric measurement taken with the Pioneer instrument, which I'll talk about in a second, through Uksana's SMASH survey in 2014. And both the stars appeared of almost similar brightness in the H-band, which was the operating regime of that instrument. And in 2019, Greg Wade revisited the system using lots of multi-epoch spectra and determined it to be an SB2, and potentially found two potential orbits for the system, both of which are rather long. The first was 18 years, the second was 26 years, and with varying eccentricities as well. And unfortunately, it couldn't be completely determined which of the two orbits was the case at that time because of a lack of data, particularly at periastron, and confusion due to the magnetic lines in the system that you can see an example of here. So what we did in our work was I revisited the system using multi-epoch interferometric data. This was using two instruments, particularly the Pioneer and the gravity instruments at the VLTI, which you can see in the top right there. And the kind of what the interferometers enabled us to do was to probe the system with very nice angular resolution of around 4 milliarc seconds in the K-band, for example, with gravity. And by fitting our interferometric observables, we're able to, resolve the components of the system by fitting, geometric models of, for instance, point sources or uniform disks to find out what's actually going on and how many stars we have in the system, et cetera, et cetera. And so what we can find is that we confirm that indeed it is a binary system, as was determined from the first Pioneer measurement back in 2014. And you can see that in our multi-epoch data, we're actually being able to see the binary moving around, particularly in this year of 2016. We can see some movement for the source. And so we confirmed that both the stars were of very similar brightnesses. The primary on average, the secondary on average was around 94% the flux of the primary. And from this kind of multi-epoch study with interferometry, we get the positions of the star over a very nice amount of the orbit. So here you can see all the position of the secondary varying across the orbit, thanks to this kind of essentially astrometric information that we're getting from the positions of the stars as probed with interferometry. This additional information allowed us to narrow down on that orbit, find a single solution. It's long, about 29 years. It's eccentric, 0.77. And one important thing that we got for the system was that it was a total mass of 56 solar masses, which we could get from the orbital fit as well. Now, something that kind of inspired us to look at the system in much more detail was this. So here you can see some information from gravity. And one key thing that we get from spectral interferometers like gravity is that in addition to that really high angular spatial resolution that I mentioned, we also get some spectral information. And so here in the K-band, we can see a very clear bracket gamma line profile here. And the power of fitting spectral interferometric data is that you can kind of determine where exactly the spectral emission is coming from. We already know from just fitting other interferometric observables, not including the flux, that there are 2 stars in the system. And so throughout our modeling, we're able to determine how much of this contribution is coming from one star or the other. And so essentially what I found is that in order to fit the data successfully, I could only allow this bracket gamma emission to be associated with the more massive star in the system, which is strange. Okay, why is one showing bracket gamma, but one isn't? And essentially, that piqued our interest because we know that the system has a magnetic field towards it. And bracket gamma has been used as an infrared indicator for magnetospheres and hot stars. And also bracket gamma could be, alternatively, be an indication of confined wind from a magnetic field as well. And so this kind of implied to us, well, okay, maybe the primary star is the sole cause of this magnetic signal towards the system. And we decided to see if we could explain that. So given the new insights from interferometry, we went back to the spectra that we had. We used and did a bunch of analysis to try and get the individual properties of the stars. First thing we did was we did some spectral disentangling to take all of those multi-epoch spectra and split them into individual spectra for each of the stars in the system. And we combined that kind of spectral disentangling work with the total mass that we got from the interferometric orbit, and giving us the individual masses of the system, which you can, of the 2 stars, sorry, which you can see here. We also did some SED fitting using magnitudes from the literature, the flux ratios we got from interferometry, and also the disentangled spectra to get in luminosities of the 2 stars. And we did atmospheric modeling of the 2 stars using the CMF-AGEN stellar atmosphere models to get further parameters of the system. And you can see these here. You can see examples of a couple of the lines that we used in CMF-AGEN fitting, and I've picked one good and one bad to illustrate to you some of the problems that we had here. So CMF-AGEN does not include magnetic signatures in the model grid, so we're never going to fit these strange Balmer line behavior that we see. However, for the secondary star, we were able to get a much more concise fit. And that's why for the nitrogen enrichment here, we could determine that for the secondary, but we could not confirm anything for the primary. So that's why there's a gap in the table here. But for both stars, we're able to get temperatures, subgravities, rotation, etc. Okay, so putting these properties that we found onto a Hertz biological diagram, we see something weird. It appears that looking at just the points for now, that the primary and the secondary are not in the same place in the HR diagram. The region that HT148937 is in is not sufficiently dense for us to think that capture could have occurred here. So that kind of implies that something strange has happened to one of the stars to make it look different to its twin. I mean, they're also otherwise quite similar in mass. So what's going on here? And so first we wanted to check if we could find single star evolution models to see if we also would see this age discrepancy. Thank you. And we do, using the bond stellar models. We also were able to see this age discrepancy between the 2 stars. We considered 2 cases for secondary, without or with nitrogen, because we couldn't determine it for the primary. And we see that in both cases, we see some rejuvenation between the 2 stars and of at least 1.5 megayear. And so that's what these contours are on the HR diagram here. And so that made us think, okay, what could have caused this rejuvenation and caused the primary star to look different to the secondary, which looks much more like a normal star. And so we're assuming that is like our reference point in the system. So we reached out to Fabian Schneider, who we just heard from, and who did some very nice models concerning stellar mergers. You can see a snapshot of one of the simulations here. And we liked this idea because Fabian showed that when 2 stellar cores can merge, you can get rejuvenation because the convective core of the merged star is large. You get mixing of hydrogen, and you get some confusion. It can make the star appear younger. And also the shear between the 2 cores of merging stars can amplify magnetic field as well. So we thought, okay, let's see if these models can help us to explain what we see. And so we reached out to Fabian and tried to see if we could replicate the age difference we see from the stars from the rejuvenation of his models. And we're using the age of the secondary as the reference here. And so again, we have 2 cases, including nitrogen and not including nitrogen. And in both cases, we can find a solution. The main difference is that the weight of the 2 stars that would have had to merge to create the primary star as we see it today. But yeah, basically an initial total merge, excuse me, an initial total mass of 35 stellar masses can explain both the present day mass of the primary star and the observed age discrepancy. And we think the nebulae joins into this quite well. Nebulae is enriched in CNO elements, particularly nitrogen, the bipolar lobes. And the estimated mass of the nebulae from previous work overlaps quite nicely with the mass lost in the merger models that we use. And so, yes, we think that potentially HT148937 was an originally a triple system with 2 stars merged to form the central, what is now the primary and now the magnetic star. And that secondary star has remained in an orbit surrounding the system, and potentially this throughout the enriched nebula that we see around the system as well. And so I'm out of time, so I will say thanks, and I will take any questions. Thank you.
Interesting stuff. Questions?
Yeah, Abigail, thank you very much for the talk. Do you see an effect of the companion on the nebula?
The nebula is very complex. It has lots of different kinds of structure. The bipolar lobe is probably one of the most symmetric elements, but there is some asymmetry in the inner regions. There's a paper by Lim that came out this year as well, where they've done some dynamical study of well, they're looking at integral field spectra of the system and looking at some movements. They derived a dynamical age for the nebula, at least of 7,500 years. But I think they kind of use like a axisymmetric model, which doesn't account for the weirdness in the middle, if I remember correctly. So there is something strange happening there. But yeah, there's more work to be done to see what's happening there.
Maybe another quick question. If I don't see any hands up, so all right, let's thank Abby again. And then we have the final speaker of this session. We have Amit Kashi from Ariel University, who I think is online. Yes.
Yes. Can I show the screen?
Yep.
Okay.
See it?
Works fine? Okay, so I'm Amit Kashi from Ariel University. I'm going to talk about interacting winds and giant eruptions in massive stars. And as the last speaker of the session, I'm exempt from telling you how important massive binaries are. And I'm not going to show any pie charts. I'm just going to get into colliding wind binaries. So when we have a colliding wind binary, we have 2 stars, one with stronger wind, one with weaker wind, and they collide and create this conical structure with 2 shock waves separated by the contact discontinuity. And this is the way it looks when you take a slice from the side. The opening angle of this conical shell is determined by this parameter eta, which is the momentum ratio of the 2 winds. This is a famous plot from a paper by Eichler and Deuce of 1993. And you can see the colliding wind structure here, but when you have the orbital motion, you lose the symmetry. You have a leading arm and a trailing arm, and nothing is symmetric anymore. Yet we are able to model such structures analytically. And the shape of the colliding wind structure can differ depending on this value of eta and the ratio between the orbital velocity and the wind velocity. And I'm going to show an example when you have such a switch in an eccentric orbit when the conditions change. So this is this very massive Wolf-Rayet binary, Melnick 34. You can look at the masses here, 147, 136. This thing is really massive. And let's see a 3D simulation of the colliding winds. You can see the shape is changing from a cone, from a wide cone, to this spiral. Here we have a value of eta of 0.69, eccentricity of 0.68. Let's zoom in on the 2 stars and the region between them, and you can see the change again. And you can see on the right-hand side the X-ray emitted from such a system. And as you can expect, it is stronger close to periastron passage. Now, this is really simple, but more effects and more effects come into play. I listed most of them here, most of them related to radiation, also gravity, wind acceleration. And the final result is a complicated colliding wind structure that changes with time. So we need numerical simulations to model it. And you can see the colliding wind structure, the way it looks in a 3D simulation from 3 different points of view, the same structure. On one side, you have, in this case, large blobs or cell. On the other side, you have fine clumps and filaments. Now, those filaments are a key of this talk. I'm going to claim that in some cases, those filaments can be accreted onto the secondary star. Everything I'm showing now is a 3D simulation. You're just seeing slices of those simulations. This is the cone and all the clumps within the cone. In some cases, mass can come very close to the secondary and get accreted. So the question we aim to solve is this accretion against stellar wind. So this is different from simple Bondi-Hall-Littleton accretion. Here you have an inflow, but you also have a star with its own wind opposing the coming inflow, and you can expect that it would reduce the mass accretion rate. And the question is, what is the mass accretion rate in this case, and what kind of accretion do we get? Is it direct? Do we have a disk? And what happens to the wind of the accretor? So to answer those questions, I started a controlled experiment. I took colliding winds with two stars. This time they are not orbiting, they are just stationary. And when I increase the mass loss rate of one of the stars, we get accretion. You see those filaments getting onto the secondary and getting accreted. This is the way it looks in 3D. You have the secondary right here, trying to push away the incoming wind of the primary and inflating those bubbles, and along those filaments, mass is getting into the secondary, and we get this accretion. Let's repeat the experiment. Twice as strong primary wind, or twice smaller the value of eta, the wind momentum accretion. Sure enough, you get a narrower colliding wind structure and more accretion. This is the same thing now with orbital evolution and a very small value of eta. So here you get that the secondary wind is basically extinguished by the primary wind, and you get a much larger accretion, and you get this column behind the secondary. Let's plot all these simulations panoramically for simulations with orbital motion and for static stars. And you can see here, this is the Bondi-Hoyle accretion region. You get a fairly constant mass accretion rate. When the wind of the secondary becomes more important, you get intermittent accretion. And if the secondary wind is strong, you get only occasional accretion. Now, let's see this diagram. The wind momentum ratio is here, eta, and here we have the average mass accretion rate. We have three different regions. This is the Bondi-Hoyle-Littleton region. As you can expect, the mass loss rate of the secondary is small compared to the primary, and we get weak. And we get the Bondi-Hoyle-Littleton accretion. Here we have no accretion at all. The secondary wind is strong and prevents accretion. And this is the interesting new thing, the sub-Bondi-Hoyle-Littleton accretion. We get accretion rate lower than that of Bondi-Hoyle-Littleton. And this white triangle, the gap between the two winds, is coming from the wind of the secondary. And very interestingly, it follows a power law. The power is not always the same. It depends on the parameters, but it is a power law. Now let's see what happens when you have enough angular momentum and we have a periastron passage. We can get a disk around the secondary, an accretion disk. It will be a temporarily disk after some time when the primary goes away or the secondary goes away. It will be dispersed by the wind of the secondary. But in the meantime, jets may form from such a disk. Let's see a different case where the secondary wind is a little bit stronger. it can push away some of this arriving material and create a gap between the secondary and the disk. This is the way it looks in 3D. We have this disk here, but you can see from the side, we have this gap. And maybe in this case, we can also get jets. This is not certain. This is the way it looks when you enhance the colors. You can get those very small filaments that get accreted onto the secondary star. And this assumes the shape of a saw blade. So if you want, we can call it saw blade accretion. Now let's talk about the jets. Let's repeat the same experiment as before, but when we have accretion, we add the jets. So the jets have a few effects. They push away the ambient mass, they heat the gas, and as a result, we can expect lower accretion rate. This is the way it looks in 3D. We have the jets here, and we have the primary material coming from the left to the right. Here is the secondary. Let's look at the accretion rate. We can see a comparison between two experiments. The dashed black line is without the jets, and the blue line is with the jets, and sure enough, you get that the jets reduced the accretion rate. And I will leave here the conclusions, unless we have more time and I have more things to show. Thank you. I'll take questions.
All right. Any final questions for Amit? Okay, we have Fabian online. Go ahead.
Thank you. Thank you very much. Hope I'm audible. So when you're going into this regime of very strong wind momentum from your primary star, naively, I would have expected that you might actually stop accreting onto the companion, but rather actually removing part of the companion star. I guess you can't see that because the companion is a point particle?
No, the companion is actually a sphere. The companion is actually modeled as a sphere that ejects material into different directions. I can actually modify the mass ejection rate from the primary also, and I can even monitor the direction from which material arrives to the secondary. And for example, in the case of the disk, you can see that more material arrives from regions close to the equator and effectively reduces the effective temperature of the accreting secondary. I'm not sure I answered your questions because there was a connection problem in the middle. So did I answer your question?
Okay, maybe I rephrase my question.
Yeah, okay.
If you have a star that is a companion and that is sitting in the strong wind, would it not actually lose part of its atmosphere? And so you do not accrete onto the companion, but you actually lose mass.
Yeah, so this is possible, you're right. I didn't model the atmosphere of the secondary in my simulations. The secondary size is fixed, and the atmosphere is not modeled, only the wind is modeled, but it is certainly possible that such an effect would happen, yes. For very strong winds, it can happen, yes.
Okay, this is a quick question.
Hi, I have a question about these jets. How fast are they, and what is the energy content? I understand they are thermal jets, right?
Yeah, so we eject. This is just an initial experiment. We take just a fraction of the arriving material, the accreted material, and create like a feedback routine that ejects some of this material in the form of jets with a fixed opening angle. And this is very similar thing to what people do in simulations of AGNs, for example. They take the accreted material and create feedback. The feedback can be thermal feedback, as you said, can also be kinetic feedback, and they both can affect and reduce the accretion. They act as a negative feedback.
All right, so we are pretty much out of time here. So let's thank all the speakers again. Next up, we got more poster sessions. So go there. You still have time to check out some posters related to this focus meeting, and we'll be back at 3:30.
3. Testing. What? Oh my God. This is probably better, I think, because otherwise you have to like, when you're pointing and it's just like awkward. Is this distance okay? Oh, is this okay? This okay? This okay? Okay.
That's
How do I make a
true,
judgment if the data's good?
well, I would assume that the referee did the job.
I never see a referee does their job.
But at least for observation, it's always how to say, you always get bad data, that's for sure.
Yeah,
good
and
data.
the error bars are really high, and do I even trust this? The observers also don't seem
But
to
it's-
trust, like in the discussion conclusion, they're like, oh, I want this but.
That's how it is. I mean, observation is kind of hard because you are limited by the number of
Yeah.
photons and the weather and so on. So
The sky. I visited the LBT and basically all the big telescopes in Tucson, Arizona.
Right.
I went on a trip with the department. I saw how big the machines are and how difficult it is.
Yeah.
How like they're cleaning the mirrors.
Yeah.
I understand it's difficult.
A lot of
this
manpower
is why I
involved
didn't
there.
do this is why I didn't do observation for this.
But there are people who are enjoy doing it. So
Do you have observation?
mostly people are observational there.
Okay.
So we use lots of telescope there.
Which telescope?
Mostly the Nordic Optical Telescope and the ESO telescopes in Chile.
How much is like Magellan?
Magellan is good. I've been there a few times.
And in the US, if you're interested in observation, you end up at has
Right,
most of the time of the Hawaiian whatever.
Yeah, with the cake. Yeah.
They have like half the time. They find they have more time than that they can use.
Okay.
So they just let the time kind of they give it to students.
But Daichi, they're also from Harvard and he's keen observer.
I have never met Daichi before.
Never met,
He's from
okay.
Harvard. Hi.
You observe a lot, so you should talk to him.
It's on, I think. Yeah. Test, test. No?
All right, I think it's time for the final session of the day, of the meeting. And we'll kick off with Access Tebunanos talking about variable massive stars. Please.
Okay, thank you very much to the organizers for inviting me to give this broad overview on variable massive stars, which includes a lot of evolved types of massive stars, as well as a lot of types of variability, such as pulsations and eruptions, which are shown in a cartoon here, and I'll get to this later on in the talk. Now, which massive stars are progenitors of core collapse supernovae? Well, let's look at the HR diagram. At the very top, highest luminosity objects, you have various types: Wolf-Rayet stars, blue supergiants, supergiant B bracket E, red supergiants, also the yellow hypergiants and supergiants, and LBVs up here near the Humphreys-Davidson limit, where a star exceeds the Eddington limit luminosity in its photosphere and is unstable, so we don't see stars there. Now, traditionally, we expect the highlighted stars we expected them to explode as supernovae. But recently, there's evidence for yellow supergiants and LBV progenitors of supernovae as well. So ideally, we'd want to have a mapping between the zoo of massive stars, the evolved spectral types, and the core collapse supernova fraction. So, or the spectral the types of supernovae, and also to match these fractions. So this is from the LIG Observatory Supernova Search with the volume limited survey within 60 megaparsecs of 80 core collapse supernovae. Now the question is, can massive star variability help determine the mapping? Well, let's take a look. I'm just going to talk about blue, red, and yellow supergiants and LBVs. I can't cover everything. I'll try and give a brief overview. So we didn't expect these two blue supergiants to explode, but since 1987A, we know that they do. 87A caused a peculiar type 2P supernova. There was a spectrum from before showing that's B3 supergiant, so that's certain. And eventually it was explained as forming from an evolved stellar merger. Now, one thing to bring up here is the blue supergiant problem, that there are a lot more blue supergiants observed than expected from evolutionary models compared to hot main sequence stars. So there are actually 100 to 1,000 times more blue supergiants than expected. So this is trying to be, there are people trying to explain this with internal mixing and mass loss, which could increase the number of blue supergiants, and also evolved stellar mergers that can produce such blue supergiants. Now, just briefly, I'm not going to go into details because this is quite technical, but there's some recent and theoretical predictions of how you can tell apart blue supergiants that's going to the left versus going to the right. So asteroseismology, it seems that can probe these radial pulsations and non-radial pulsations and period spacing. So these are predicted to help distinguish these post-red supergiant, blue supergiants. That's a tongue twister. So we can look at the post ones, and those are the ones that could explode. Now here's just an example of some data from TESS. So this is from a recent study by Ma. They had 20 blue supergiants with TESS data. They computed amplitude spectra, and they found stochastic signals. So what you see in the blue, the low frequency signal, and they're all explained by damped gravity waves excited from the convective zone and caused by the iron opacity peak. So this is a promising method, especially with data from Plato in the future, may solve this blue supergiant problem. Moving on to yellow supergiants, these are associated with type 2b supernovae. Some examples are listed there. And again, here's a recent paper, Don Wallenstein et al. So this is an HR diagram, but a bit unusual. Instead of showing the positions of stars, they have power spectra of 76 cool supergiants in the LMC. These are again from TESS, and they show that they found that the strongest signals were found in this new category of, they call them fast yellow pulsating stars. They have periods under 1 day, and they're stated as being candidates for post-red supergiants again. So this is a way again to find these post-red supergiants that are of interest to the supernova community. They also found that all their stars have some stochastic low frequency variability, similar to that in OB stars, and attributed to internal gravity waves. Luminous blue variables. So these are very big categories. I'm just briefly touching the surface because I can't in 19 minutes do everything. So LBVs are associated with type 2N supernovae and supernovae imposters. There are multiple types of variability, ranging from days to centuries. They also undergo eruptive events. The most famous of these are Eta Car and P Cygni. And to the right, I have a R71 here in the LMC. So this is one of the LBVs in the LMC that underwent an outburst in 2012. So this is over 10 years. And here's an HR diagram showing R71 during the outburst, where it's cooler and more luminous, and in quiescence, where it moves there to the left to hotter temperatures. So they also undergo Esterades type variability. So they vary by a couple magnitudes at relatively constant bolometric luminosity. This is due to effective temperature and radius variations in the star. So this is a brief overview of what we see. Now, what are luminous blue variables? Now, for decades, the Conti scenario was the prevailing scenario, that they're a transitional phase to helium burning. So you had O stars that would develop these optically thick, strong winds that would strip the hydrogen envelope, and that's how you got the Wolf-Rayet stars. That was thought. But then there's some problems that came up as observations and theory developed. The Esterades brightening events were eventually explained by envelope inflation or pulsation, not by pseudo photospheres of optically thick winds. Some progenitors were identified as LBVs, so they can't be, so they have to be evolved. And also the work by Smith and Tobelson here showing that the LBV environments are isolated. So they're not following the O stars as expected, so they're a different population. So the prevailing scenario at the moment, summarized here in this work, is that LBVs are evolved massive blue stragglers that have been rejuvenated either by merging or by gaining mass in a binary system. So if you have a binary system, one star is the donor, it loses mass. So this is how you get the Wolf-Rayet and eventually the stripped core collapse supernovae. And then you have the gainer that appears as an LBV or a supergiant B bracket E that when it explodes leads to a type 2Ns. So now the outburst that we find in the light curves could be triggered by variations in helium opacity, according to this study here, or merger events, which was recently proposed as the scenario Veda Carina to actually be a merger. The great eruption was a merger of a binary in a triple system that caused all this. So also to look at some asteroseismology data. So this seems to be the new thing. I don't work on this at all, so if I skip something, please let me know. This is an example of P-SIG. This is the bright constellation 5-year light curve. And again, the power spectrum on the bottom here showed stochastic variability caused by internal gravity waves, but the amplitudes are larger. The lower and the characteristic frequency is lower than the yellow supergiants and the blue supergiant I previously showed. So these authors, so this is also a recent paper, Elliott 2024, so the LBVs are an extension of the blue supergiants in the context of stochastic low frequency variability. So putting everything together in the HR diagram, you have the LBVs, you know, moving here, the LBVs up here, you have the cool hypergiants down here, and of course, they're rarely crossing the Humphreys-Davidson limit. And trying to piece all this together and see how they connect, which ones are going to explode. Now, it's not very clear how all this variability is related to the pre-supernova variability detected in some LBVs, which is very sparse right now. So this is unclear. Moving on to red supergiants, which is closer to what I've been working on recently with our group. These are associated with type 2Ps and 2L supernovae, as we all know. Morphologically, the light curves can look like this: irregular variability, longest secondary periods, semi-regular type C variability here. The last type of variability is due to pulsation of the star. And the long secondary period is not really understood from what I've been reading. The irregular is probably due to these convective cells that are bubbling up and changing all the time. Now, some things to keep in mind about red supergiants is, of course, the red supergiant problem, which has been discussed quite a lot. We don't know what happens to the more massive red supergiants. How do they evolve? But some open questions that are very related are, of course, the mass loss rates. So for this, the Kostas Adoniadis paper, which shows the increase in the mass loss rate at higher luminosities, which seems to be, I think, a robust result. The role of episodic mass loss is unclear. And of course, how does binary evolution affect the outcome, which there are many channels here. I also want to mention the Levesque-Massey variables. There are only a handful of these known. They occur in low metallicity galaxies, so far at least from what's been detected. And these stars actually change spectral type. They have very large changes in spectral type from K0 to M4 within a year. So this star seems to be very unstable. When it's in M4, it's actually to the right of the Hayashi track. So it's in a place where a star shouldn't be, it's unstable. So they're undergoing some kind of instability, and the reason is not clear. So keep in mind these occur. Other strange behaviors of red supergiants, we have the great dimming of Betelgeuse, which it was named in 2020. So it dimmed by 1.25 magnitudes in early 2020. This was explained by an anomalously hot convective plume that rarely occurred, but it's also kind of natural to occur in a turbulent atmosphere that broke free and caused the surface mass ejection. And the cartoon here is about Betelgeuse, which I showed at the very beginning. So you have this plume, this hot convective cell erupting as it moves farther away, it forms dust. Now it happened to be in the line of sight toward Earth, so we saw a dimming event until the dust dispersed and Betelgeuse recovered. Are there other such dimming events? Well, I found this work in the literature. In M51, there's been a report of of a drop. This was a search, HST search for failed supernovae, and they thought one disappeared, but then it reappeared. So this is an upper limit, and this is possibly a dimming event, although there's not much data. Moving on, this is some of our work from my student Gonzalo Munoz Sanchez. It was just accepted 2 days ago. So it's on the archive as well, so you can take a look. So this is one of the luminous stars that we had studied previously in the group. We found archival HST data showing this. There was a bar feature, a very interesting feature, which reminded us of Betelgeuse, which has a similar bar feature, and it's also run away with a bow shock. It's also very luminous. It's up here in the HR diagram, so near the limit of observed red supergiants, the highest luminosity red supergiants observed. So we studied it further. We obtained spectra. So the idea is there a bow shock? We took some spectra and indeed found shock material in between the bar and the star, and also did a Gaia proper motion analysis, which showed that the star indeed is moving in that direction, giving the various assumptions from Gaia, but they all point in that direction. So we have very strong evidence, but because it's in the LMC and this is HST data, we can't resolve it, and the star is saturated here. So we need a coronagraph, maybe from James Webb to observe it. Now, I want to focus here on the light curve. I'm not going to talk anymore about the spectroscopy or show any of that, because what Gonzalo did here is assemble a 30-year light curve of the star. So this is archival data. It was there. No one had looked at it. So in the top panel is the light curve from Macho, ASUS, Ogle, Assassin, Gaia, and Atlas. And in the lower panel, we've just subtracted a mean value for each light curve so we can compare the different filters. Now, we also, the spectra are shown in vertical lines here, the epochs of the spectroscopy. And what we found is 3 dimming events. So one here, 1999, 2011, and 2022. And we actually had spectroscopy during that. So looking at them closer up, we actually noticed that they seem to have some recurrence period of 11.8 years. That's strange. We compared to Betelgeuse, which the gray point. And Betelgeuse recovered much faster than this other star. So we're wondering why. Sorry, this is interrupting. 200 versus 400 days. I'm not sure why. We decided to check some other red supergiants, and did. MuSEP had a light curve in the archival data. We looked, very nice agreement to our dimming events. RWSEP, even better agreement. So all broad, and they agree with this W60B90, not Betelgeuse. So we're wondering why this might be. And what is the obvious thing to think is the size of the star. So if you have these convective cells that are big on the star and there's some eruption, then it takes a while for a bigger star to recover, whereas a smaller star might recover faster. So this is what we're thinking is happening, that the rise time does depend on the size of the star. And this is actually really cool because for galactic stars, you don't know the distance or the radii. You can't measure things very accurately because the distances are unknown, but in the LMC you can. So if this turns out to be true, then you can measure the radius from the light curve and the luminosity, and this is pretty cool. But we haven't investigated that further. We plan to. So how common are these dimming events? That's also unknown, but there's a lot of data out there that we would like to look at. And now I'm going to move to this WHG64 object in the LMC that Emma Bieser mentioned as the dust-enshrouded candidate. So we have some news about this one. This is Gonzalo's actually current paper in preparation, which we hope to submit soon. He assembled again a 30-year light curve, which was available from Macho and Ogle. And here we have a very, very big surprise, and also from spectroscopy that obtained, that it was a red supergiant or hypergiant for at least 30 years, but now suddenly the new spectra show that it's a supergiant B bracket E. And we're really trying to understand what's going on here. You can see the nice Myra-like variability that turned to semi-regular-like variability, and then around 2013 and 14, it stopped. And now it's kind of flat with a few bumps in it, and now it's dropping. We don't really know, well, we have some ideas, but this transition happened very quickly without an outburst or an explosion. Oh, I didn't show the spectra, right? So this M7 beforehand, and here's the supergiant B bracket E. So the 2016 spectrum actually has emission lines, and the 2021 spectrum has P Cygni profiles. Some ideas that we're investigating are that the stellar atmosphere, perhaps part of a common envelope, dispersed following a merger event. It's like it was thin and it just dispersed. It happened fast and without an outburst. So, or it could be some extreme symbiotic system. There's an object M33, object X in M33 that's very luminous in the infrared that turns out to be a symbiotic. So that's why I put that down. So these are the binary star scenarios. If it's a single star, could there be some instability due to the proximity to the HD limit? That's unknown. Everything's up in the air right now and we're investigating. So that's a sneak preview. Moving on to nearby galaxies. So this was work we've done with this ERC-funded ASSESS project. The goal was to obtain 1,000 spectra of evolved massive stars to look for episodic mass loss. We managed to find 127 red supergiants in these nearby galaxies. So this is actually the largest sample of red supergiants outside the local group in low metallicity galaxies. Here, luminosity and radius plot showing the stars we were able to measure luminosities from. And you notice WHG64 is also labeled on there, and there's some other stars in the vicinity and even higher than the 5.5 log luminosity, log L of 5.5, that's the observed upper limit. So they're definitely worth further investigation. And the circles around those points just mark those that are highly variable. We actually checked mid-infrared variability as well, and any optical variability from Gaia and past stars, whatever data we could find. On the right, I show color magnitude diagrams from Spitzer, so 3.6 minus 4.5 and 3.6. This is actually how we did our selection of targets. We wanted dusty targets, so red supergiants that have dust should be within this box approximately. Now this is zoomed in here on the right. And we also label here the spectral types that we measured from our spectroscopy with VLT. So K0, yellow. 4 stars have been labeled, 1, 3, 4. These have K type, so early spectral, which were not expected for dusty mass losing stars that we expect here. So altogether, it's like 12% of the K-type sample seems to have experienced some mass loss reduction, or perhaps they're these Lebesgue massive variables that we don't know the physical mechanism of their variability. And I also wanted to point out that these luminous red supergiants with mid-infrared variability up here have similar properties to the progenitor of the supernova 2023 IXF. So that's been quite interesting. So they're varying in a similar way in their as luminous. Okay, so future. Well, the variability of evolved massive stars definitely hold clues to their evolutionary state and may predict which are imminent progenitors. That would be really neat if we could reach that stage. Now we're also we're hoping to soon release a catalog of 1 million evolved massive stars in 26 galaxies. This is based on the machine learning algorithm by Grigoris Maravellas. It does really well with red supergiants. With other types of stars, not so well, but hopefully it will be useful. In the future, large spectroscopic surveys and high cadence of precision surveys will help, as I mentioned before, with the blue supergiant problem. And finally, the availability of long-term light curves is going to be, we're going to be able to create light curves like this for all kinds of evolved massive stars and maybe use them to identify the targets and potential supernovae progenitors. So this is also from a work of my postdoc Stefan De Witt, late type supergiant in NGC 6822. So almost 10 years of a nice light curve with perhaps some dimming events in there. So stay tuned. Thank you very much.
Thank you. Right, thanks so much.
Sorry, and this is the team that I should acknowledge behind all this work.
Yeah, thank you for the talk. I was wondering what are the typical distances of those host galaxies in this catalog?
About 1 to 5 megaparsecs. Yeah, nearby, because we're using Spitzer data and we can't really go farther than that with Spitzer. Yeah.
More questions?
I'm very intrigued by the star that changed into a B brackety. Do you have a sense of how common this might be? How common this might be?
How common? It's the only one we know of. There's some yellow hypergiants that are transitioning a bit, never from a red supergiant to anything so blue. Maybe red to yellowish, but not to blue.
No, are there a lot of observations that might allow us to see this kind of transition? Or?
Some follow-up of red supergiant via spectroscopy, although you might have to go to more distant galaxies to find enough sample to find something like this. So I think you have to monitor the extreme red supergiants, these dusty ones. Yeah, they might, other ones might be doing this. Yeah.
Thank you.
But we have time for one quick question. No? Okay, let's thank Ansiste again. Thank you so much. Next, we have Maria Arias, who will be presenting online, I believe.
Hi, I'm sharing. Okay.
We see
You can see, I need to, oh. Okay. You can see my slides okay, right? And you can hear me okay?
Yes.
Okay. Well, good afternoon. My name is Maria Arias, and I'm a postdoc in Leiden University. I would have really liked to be there in person, but I'm happy to join remotely. So my talk is going to be quite different because I'm going to discuss inferences that we can make about the progenitor star from observations of the supernova remnant in a timescale of thousands of years post-explosion, and in this case, through the imprint on neighboring molecular material via millimeter observations. So supernova remnants transfer the energy, momentum, and synthesis products of a supernova explosion into the ISM. And the supernova remnant is itself the interaction between the supernova blast wave and the stellar ejecta and the surrounding medium. So first, the supernova remnant, the supernova blast wave encounters the circumstellar material that the progenitor star sculpted during its lifetime, in particular in late stages of evolution, and that's affected by winds, mass loss episodes like the ones we've been hearing, binarity, and these environments can be complicated. And then the supernova remnant also interacts with the interstellar medium. It shocks it, heats it, and affects its composition. And we understand that this injection of energy eventually triggers star formation in a process that we call stellar and supernova feedback, but the details are still unclear. And the way that a supernova remnant looks is affected by the CSM, the properties of the explosion, including the presence of a compact remnant that can power a pulsar nebula, and like the case of the crab here, and then the dense ISM that surrounded the star. However, it's very difficult to tell apart the contributions of these different effects on the morphology of a supernova remnant. Okay, so this is a source that I'm going to discuss. It's called BRO 420501, and it's in the direction of the galactic anticenter. It's in our galaxy. And the morphology with these two structures that are called the shell and the wing in the literature is strange if we think about it as being the explosion of a star. On the gallery here, you can see that the radio emission is coincident with the optical. The supernova remnant is in the radiative stage, which is associated with older supernova remnants or denser environments that slow down the shock to radiative velocities. Note that many features are visible in the infrared as well. And in addition to the shape, there's an additional complication in the source, which is that in the X-rays, you can see the centrally peaked you can see my mouse, but you can see the centrally peaked X-ray emission that is difficult to explain from a supernova remnant because at the late stages of supernova remnant evolution, the stellar ejecta has expanded adiabatically and the material internal to the shock is low density and cool. So you wouldn't necessarily expect central X-ray emission. It's hard to explain, but it's not unheard of. And in fact, we know approximately 40 such sources, and we call them mixed morphology supernova remnants. So in this class of mixed morphology supernova remnants, a common feature is that the remnant appears to be interacting with nearby molecular clouds. So it's no surprise that core collapse explosions happen close to molecular clouds. It can be the parent molecular cloud or other clouds from the giant complexes that the star could have been born in. But unambiguously establishing interaction between a remnant and a cloud is not necessarily straightforward. I've listed here some lines of evidence that we follow from the strongest to the most circumstantial. An OH maser emission is the clearest proof of interaction because the conditions required for the masing are rather specific. And in the case of these types of sources, the mixed morphology remnants, there's a number of OH masers detected. Gamma ray emission is also taken as evidence of interaction because the cosmic rays accelerated in the supernova remnant shock require a dense environment to interact with and result in a gamma ray emission. So here in the top figure, we see a mixed morphology supernova remnant in gamma rays, and the authors have tried to establish a link between the supernova remnant morphology, which of course is affected by the presence of a dense wall that disrupts its symmetry, the gamma ray emission, and the presence of a cloud. So leaving the mixed morphology question aside, I'm going to focus for now on the peculiar morphology of the source with the two parts that are symmetrical and that have a straight line in the middle. So remember that I said before that what a supernova remnant looks like can be affected by its CSM, its ISM, and the properties of the explosion. The first set of models is from the 1980s, and they propose that the ISM is responsible for the morphology, so that if the explosion happened in a multi-component medium with different densities, including a tunnel that is hot and very diffuse, then it could result in this shape. However, over time, we have not really found evidence suggesting that indeed the environment looks like this. And we had the idea that the triangular shape could be due to a bow shock. If the progenitor was moving supersonically, and if the bow shock can survive the shock passage, then it could retain this shape. Chiotelis and all in Athens later expanded on this idea that the pre-supernova properties of the star instead of the ISM could be responsible for the shape of the source. And they added a stellar wind that could create the medium, in this case, circumstellar rather than interstellar, that would give rise to our supernova remnants morphology as it expands. So what I set out to do was to study the dense environment, and we looked at molecular gas over the course of 2 IRAM campaigns. So we first looked at the upper right corner of the source. We had data with different transitions of carbon monoxide, and we didn't find evidence of the shock encountering and heating the molecular material, but we did find a disturbance, and that's this sweep here on the corner, in position velocity space that is indicative of a bubble in molecular gas. And there's an empirical relationship between the radius of a wind-blown bubble and the mass of the star responsible for it, although we've heard many caveats about it during the sessions. But using that, we inferred a progenitor mass for this remnant. So it doesn't take us very far because, of course, there are many stars in the 12 to 14 solar mass range, but it's not easy to tell the mass of the original star typically in a supernova remnant that's a few thousand years old. So we continued and we took more data corresponding to the southern part of the footprint over here on the left. And on the right, you can see some regions that we identified as showing disturbed molecular material. In the regions highlighted in red, the coral line, which is the J2-1 transition of carbon monoxide, is higher than the blue, which is the J1-0. But in order to get the observed ratios, a shock must have encountered the material. And for these lines, it's the supernova remnant shock. All the remaining lines are indicative of heating and compressing, but not to the same extent as the ones in red. And you can see that the ones in red are also bright at 12 microns. So in addition to the regions that show spectroscopic signatures of interaction, we found more of these sweeps, which are due to the material being pushed but not shocked or otherwise recombined after the shock, except for the sweep here in region A, which is still shocked. These are indicative of a stellar wind or of different stellar wind episodes that are sweeping the molecular gas. And we think that this is also the case for the regions where the molecular lines show disturbances due to a shock that's not quite as strong as the supernova remnant shock. So here in the infrared map on the right, I've overlaid the features that I've shown in red, and in blue are the ones that are due to the wind. And you can see that the blue features are consistent with an equatorially enhanced wind, as Chiotelis proposed in his model that I told you about earlier. So the time is really limited for this talk, and I'm sorry if it's a bit superficial. I'm going to end here. But basically what I want to highlight is that it's possible to learn something about the progenitor from the 1,000+ year old remnant, but the evidence is very patchy and we need to rely heavily on modeling. What's interesting about this approach is that there might be other sources like it where the imprint of the progenitor lives on in the morphology of the source for longer than expected. So I'm going to stop and take your questions.
Thank you, Maria. Questions for Maria?
Yes, I'm wondering for the better known SNRs like IC443 and W44, don't we have interesting constraints of similar kind regarding the progenitor? I don't remember. Huh?
You mean from their morphology?
And also the location of like molecular material and also maybe the wind properties or some hints of the stellar wind. No, on IC443.
Yeah, so both IC443 and W44 are interacting with their neighboring clouds. So I guess that tells you what the position of the supernova remnant shock is. But as far as I know, there aren't these sweeps of imposition velocity that are indicative of the bubbles. But it would be something to look into, and I'm sure it can be done with archival data because these sources have been observed very thoroughly.
Hi, Maria.
Hi.
Thanks. Really nice talk. I'm really excited about this bow shock idea. What was the velocity that was assumed in Geertellis's model for the star? And can you say a little bit about the density of the ISM?
I don't know what was the velocity that was assumed. I think I want to say something of the order of tens of kilometers a second. And for the density, I also don't know what he assumed, but I think possibly something around 1 particle per cubic centimeter for the ISM density.
Okay. Yeah, let's thank Maria again.
Testing. Okay.
Next, we have Shelley Cheng.
All right, good afternoon, everyone. My name is Shelley J. Chang, and I'm a 4th year, starting my 5th year grad student at Harvard University. And I'm very excited to share my work about a model of eruptive mass loss in massive stars with you today. This work has been in collaboration with the Simons Foundation, also known as the Flatiron Institute, also known as the Center for Computational Astrophysics. So yeah, to start off, I will give a very quick overview of why massive stars matter. I think I'm kind of preaching to the choir here. Everyone here already agrees. So first off, we see very beautiful bow shock kind of behavior in the night sky. So here I'm showing Zeta Ophiuchi, which is the closest O-type star to us. And there's this beautiful bow shock. So first reason is that they create beautiful things in the night sky. However, they're also very important in other fields, such as galaxies, compact objects, and supernovae. So for the case of galaxies, massive stars alters the density and overall movement of matter in galaxies, which alters star and star cluster formation. And of course, stellar winds contribute to feedback, which is very important. For compact objects and supernovae, massive stars are the precursors to these objects. So for example, the mass loss of helium stars can help us constrain the starting masses of black holes and neutron stars, which they can then use to study gravitational waves. In the case of supernovae, pre-brightening phases of type 2n supernovae are associated with post-main sequence mass loss of massive stars. So yeah, massive stars are important. So observationally, one type of massive star that is quite interesting are red supergiants. So we observe this 20 to 30 solar mass upper limit. So this is derived by a luminosity upper limit observed. And so here I show Betelgeuse, which is a very famous example of a red supergiant, which we all thought were going to go supernova last week or last year. However, so this type of mass loss that red supergiants kind of undergo is thought to be, the reason behind this 20 to 30 solar mass upper limit. However, the details of this kind of post-main sequence mass loss is not well understood or well constrained. So if we move to higher masses, we become luminous, blue, and variable, so LBVs. And these LBVs exhibit another form of mass loss, eruptive mass loss. So here I show a example. This is AG Carinae, and I want to emphasize that this is still a star, and there's this huge shell of material around it. And LBVs exhibit mass loss of 0.1 to up to a few solar masses per year, which is incredibly high. And this is only sustained for around maximum 10 years. Otherwise, we won't have a star anymore. However, this type of mass loss is very interesting, very shocking to see. However, it's not well understood again. So some 3D simulation work has been done to better understand LBV mass loss. So here I show a plot from Zhang et al.'s 2018 Nature paper, where they ran 3 simulations of wedges of stars undergoing eruptive mass loss. And the 3 simulations cost them over 60 million CPU hours. So incredibly expensive, very detailed simulations. And the main conclusion from their work is that helium opacity peaks in the atmosphere can drive mass loss. So if you can look at the left side of this plot, this is gas density in CGS. It's very much not spherically symmetric. You can see the giant plumes in purple. However, because of the computational cost of 3D simulations, I think it is important to explore lower dimension modeling to study a single star throughout its entire life or many stars throughout their lives. So that motivates our research questions of, can we actually understand eruptive mass loss in one dimension? And can we estimate a mass loss rate? So to do this, we use MESA, which is a stellar evolution code. It has a lot of different ingredients, and we're focusing on stars from 10 to 100 solar masses at SMC and solar metallicity. So for our mass loss recipe, there's kind of 2 things happening at the same time. So first off, we have these continuous winds, which we've heard a lot about. This occurs throughout the evolution, has typically lower mass loss rates. And secondly, there's this eruptive mass loss that I mentioned in the case of AG Carinae, and it only occurs during part of the evolution and has much higher mass loss rates. For this continuous wind model, we employ the Dutch model, so the authors are all from the Netherlands, and this model relies on many different factors such as metallicity, mass, luminosity, and effective temperature. It is a line-driving wind model. So quite simply, photon hits an ion, momentum is exchanged, and it drags hydrogen and helium out along with it. So line-driving wind. This is much better understood than eruptive mass loss. Speaking of which, for our eruptive mass loss model, we kind of form an understanding of how energy is transported in a star first. So the 2 major ways are radiative diffusion and convection. And now I'm going to show this, how we're going to walk through it. Let's focus on the x-axis. It's just log of t, so surface on the left, core is off the axis on the right. Vertical axis is gamma factor, which is a luminosity over the Eddington luminosity. In green is the radiative luminosity, so the luminosity carried by radiative diffusion. The black line defines where the ratio is 1. So everything above the black line is locally super Eddington. And then the red dashed line, vertical, is a kind of critical optical depth that we define that separates regions where convection is and isn't efficient. So if we want mass loss, we're looking at this region. So it has to be locally super Eddington so that the mass has a reason to leave. And it has to be shallow enough for radiative diffusion to take place so it can leave. So specifically, we're actually going to compare some kind of total integrated excess energy from that locally super Eddington luminosity. And we're going to compare it with the binding energy of the overlaying envelope. So more formally, in equation form, the critical optical depth is C over V sound, so kind of photon leave. And we're going to use our dynamical time throughout the equations to turn our luminosities into energies. And we're going to add this squiggly xi factor, a Greek letter, in order to tune our model. So this is a quite simple energy-based model for eruptive mass loss. Now, with the 2 types of mass loss that I mentioned, the continuous winds and the eruptive mass loss, this is how they kind of work together. So here I show a mass loss rate over time, and this is an HR diagram of the same system. In red is that eruptive mass loss, which only occurs during part of the evolution, whereas the black Dutch continuous wind occurs throughout. So the black is underneath the red here as well. So this kind of behaves as we expect. And okay, so now onto the full results. Here I show HR diagrams with gray tracks representing a single star evolving from main sequence all the way to core helium depletion. And I show in color contours here the mass loss rate of eruptive mass loss in units of solar mass per year in log scale, right? And you can see that the mass loss occurs, the really strong mass loss occurs in a strip between 3.5 and 4 log T effective. And so this mass loss rate is here. And on the left plot here, I have a squiggly xi of 0.1, so only 10% of the model efficiency I showed previously. And on the right, I have a xi of 1, so at the full kind of model strength. On the left-hand case, you can see I still get my red supergiants here. However, on the right-hand case, I no longer have my red supergiants. So this suggests that perhaps eruptive mass loss in this form can contribute to the lack of red supergiants above 20 to 30 solar masses that I mentioned in the introduction. To more clearly see this, here I plot the evolution track difference. In purple, it's just continuous wind only, whereas in black is the version with eruptive mass loss. You can clearly see how the stars do not end up as red supergiants and this can turn back and may end up as blue supergiants or yellow supergiants. At a lower metallicity, it's a similar kind of story, however, it's not as clear. So on the left, you still get some red supergiants, on the right, no longer any supergiants. So therefore, in conclusion, we have a successfully modeled eruptive mass loss in massive stars with this kind of physically based energy model in MESA. And eruptive mass loss may be a physical mechanism behind that missing red supergiant. All right, so this paper has recently been accepted as of yesterday to AppJ, and the in-lists are all available on Zenodo as of last night. So thank you so much for listening to my talk.
Thank you. Do we have questions?
Thank you for your talk. It was especially interesting for me because in 1972, many years ago, I published a paper in Astrophysical Space Science, which was called Evolution of a Massive Star with Mass Loss. It was a calculation of evolution of 30 solar mass star from the main sequence until the stage where a static model failed, and we constructed a self-consistent model with mass loss. And m dot was an eigenvalue, and to our surprise, it was very high, few percent of solar mass per year. And the physics was absolutely the same, high peak of opacity due to recombination of hydrogen and helium.
Yeah, thank you. Are you talking about the geyser model? Because that is a model that I've seen previously in literature, where it's a similar kind of concept. However, the difference between that model and ours is that assumes a timescale much shorter than the stellar evolution timescale for the mass loss, and therefore it's hard to integrate that specifically into stellar evolution codes. So is that what you're referencing? I'm not quite sure.
I'll give you a reference to the paper, which is a detailed description of the model.
Of course, thank you so much.
Thanks. Very nice effort to finally put something that one can plug into MESA there. I was wondering actually two things. First, like I guess you stayed with the Dutch recipe just to compare to old models, because I wouldn't recommend to use that in particular at lower metallicity anymore without further modification, and you see where your tracks are going. And the second thing is, are you planning to deal with the effect that when you get closer to the Eddington limit, you should also have enhanced winds before you might trigger eruptive mass loss? Because it looked a bit from these results that you might overshoot a bit too much in some of the results with the eruptive approach.
Yeah, so first part of your question in terms of the use of Dutch. So we use Dutch primarily so that it can be compared with previous works. We use a Dutch scaling factor of 0.8 as well, because many different papers recently have used that. Second part of your question about the overshooting of mass loss. So this is kind of why we have that squiggly xi factor. The follow-up work is that we're going to look at some observations of real red supergiants and some real data and get a better handle of what that xi is. Xi may be mass dependent and maybe a lot of things dependent, right? So we hope to kind of include those effects in the xi factor. If not, then include it separately as part of the MESA in-lists. Yeah.
Okay, I think we have run out of time, so let's thank
Thank
Jelly
you.
again. Next, we have Castelli. I don't know if I pronounced that right. Connecting online, not this one. Yes, he's online.
Okay, hello everyone. My name is Joel, and I'm currently a postdoc in Japan. So today I would like to share with you our work on numerical simulations of silicon shell burning in massive stars. And this stage is basically just a few minutes before the explosion of a star. So here I listed a couple of my main collaborators and students, and the work that I'm focusing on today is in particular in collaboration with Tomoya Takiwaki-san and Ko Takahashi-san. So the story starts with the neutrino detections from supernova 1987A that basically gave support to the neutrino-driven explosion model. And as you can see in this figure, neutrino heating plays an important role in increasing the shock radius, which could lead to a successful explosion. However, if there is no convection in the model, the shock radius actually does not grow further. So we see that there is also a very important ingredient to have the asymptotic growth of the shock radius, and that is convection. So one way to quantify convection is through the Mach number. And in this formalism, there could be a direct relation between the Mach number and the shock radius. What this effectively means is that convection in the supernova simulations can determine whether the model will or will not explode. So it's important to depart from 1D models and use 3D simulations, including convection. But it's also important to depart from spherical symmetry. It turns out that in some cases, even if 3D models are used, models will not explode if they are spherically symmetric. And what this means is that, in turn, there are cases where an initial seed instability or perturbation, if included in the models, will produce a successful explosion. So not only we need to move the problem to 3 dimensions and include convection, but we need to have seed instabilities in supernova simulations that will aid the neutrino-driven explosion. And this is one of the reasons why, in recent years, numerical simulations in advanced burning stages of massive star evolution are gaining momentum. And several studies focus on hydrodynamic simulations, studying convection. But it's also important that all physical ingredients need to include magnetism and rotation as well. So our goal is to focus on the silicon burning phase around the iron core and include all these physical effects in 3D models. In order to do that, we first compute a 1D base grid of models. And in these models, this is a quite large parameter space, we search for the best scenarios that we believe will produce strong convection in 2D and 3D. And then we look at the 2D models, about 100, 200 of them, and find only a few that will follow in 3 dimensions. Obviously, the high computational cost means that we can only compute a few of them. So we have about 10 3-dimensional models, but I would also like to add that we still need to run them for longer times. So some of the results here are preliminary in that sense. Okay, so this is how it looks like. This is a 3D MHD model with rotation. And the figures here show snapshots from the evolution. So the time increases from left to right. And the colors correspond to the iso surfaces of entropy, which is a quite good measure of convection. In fact, the simulation is quite reminiscent of a magnetorotational core collapse model, but it is not. It is still a few hundred seconds before it would explode. So what we see here is primarily the effect of rotation. It forces convection to be in a jet-like structure around the core. And as time progresses, there will be a more homogenized region around the core, but on the large scale, there are vortices, and so material and convection will take place preferentially along the rotational axis. This is also quite apparent if we look at the silicon distribution in the model. So initially, silicon will be basically streaming out away from the stellar core and crash into an oxygen-rich layer. As time progresses again, the material at large scales will be more mixed, but we actually also see that there is a very strong silicon-rich layer around the iron core in this case. In fact, as I said before, here these are the effects of rotation. We need to run the simulations longer to see the effects of the magnetic fields. Now, if we compare this case of the MHD model with rotation with the, let's say, control experiment, where we only have a hydrodynamic model, but no rotation and no magnetic fields, then we see that initially we start with a relatively spherically symmetric case, and then the well-known structures, the plumes of convection, will develop, and complex flow patterns will characterize the region around the iron core. So this is indeed the region where we expect those asphericities to develop and will aid the subsequent supernova explosion. So if we look into the silicon abundance in this particular case, we see that initially there are pockets of overdensities, and convection is very efficient in mixing material. So as time progresses here, we see that on the large scale, the silicon abundance will be well distributed, even though there will be regions of slight over and under densities. The other point is that here we see that the silicon-rich layer grows in size. So convective mixing will efficiently increase the silicon layer around the iron core. And this is important, for example, for shell mergers. So what you see here are profiles, radial profiles as a function of time of silicon, oxygen, and neon. And in the 3D hydro case, we see that the growth of the silicon-rich layer actually also contains a lot of oxygen. And we can talk about a shell merger here because this layer will contain silicon and oxygen almost equally. It's actually also interesting that some neon is also mixed into this region. And there are at least two important implications. One is that this has observable consequences. If one studies the supernova ejecta, then the abundance ratios can be used to actually infer these kind of shell mergers. The other point is that if we look into the impact of shell mergers, then the size of the convectively unstable region increases. So by increasing the unstable region, we will have higher Mach numbers. And this is important because the higher Mach numbers correspond to higher shock radius in the supernova simulations. So this will be preferential the site that will produce those seed instabilities and perturbations that aid the neutrino-driven explosion. So we are indeed finding some evidence that there is the silicon-rich layer around the iron core that is convectively unstable and has the potential to trigger those instabilities that will lead to successful explosions. So I will stop and summarize here that we are studying the silicon-rich layer around the iron core in massive star models, and we want to investigate all physical effects, convection, rotation, and magnetism together. And we are finding evidence that the layer around the iron core is strongly convective, and this is important for the asphericities in the subsequent supernova explosion. We are also seeing cases of shell mergers, which have interesting implications. So thank you very much for your attention, and I'm happy to take any questions.
Thank you very much. Any question for Joe?
Thank you for interesting talk. At one of your slides, there was a magnetic field equal to 10 to the 9 Gausses. Could you please comment why do you choose this value of magnetic field, and what was the configuration, initial configuration of the magnetic field? Thank you.
Right, thank you for the question. So basically, we assume this kind of magnetic field to support the supernova simulations that will precede this. In general, the supernova models use a similar strength of magnetic field. So we believe this is an appropriate assumption here. And for the configuration, we are using also a similar structure, a quadrupolar structure that has been modeled in supernova simulations.
Okay, any more questions? Well, I have one. You mentioned that some signatures can be seen in the supernova ejecta. Do you know where to look and which element, for example? And what are
So I think the Sato et al. Paper is a very good reference for that. I think the neon and magnesium ratio would be a very good tracer of this in particular. So one would need to look into basically the ratios of different elements to try to infer the occurrence of these shell mergers.
All right, thank you so much. Are there more questions? Okay, there's one last one.
Thank you. I have a curiosity about the resolution for get the development of these instabilities. What is the maximum resolution for observe that?
Yeah, so we haven't performed a resolution study yet. In 2D, we have checked a few cases, but not in 3D. So this is one of those issues that in 3D, this is extremely computationally expensive to test. And I suspect that it's better to actually start in 2D, but we haven't checked the impact of resolution yet.
All right, let's move on and thank Zsolt again. Next, we have Agnieszka Janiuk.
Microphone? No. Okay. Good afternoon, everybody. My name is Agnieszka Janiuk, and I am leading the theoretical astrophysics group in the Center for Theoretical Physics in Warsaw. And the work I want to present today has been done in collaboration with my former master student, Dominika Król, who is finishing her PhD now at Jagiellonian University and is about to start a postdoc at Harvard CFA. And I also co-supervised remotely the postdoc from Iranian National Observatory, Najesh Shahamat. Okay, how do I change the slide? Sorry. Green? Okay. Sorry, green button is the easiest one. All right, so the transients I have in mind are gamma ray bursts. So we had yesterday beautiful talks about gamma ray bursts, so I will not repeat the definition. They are long gamma ray bursts, which I will focus on, originate from collapse of massive stars. And most of them exhibit in their prompt emission strong variability. You can see that on the gallery of light curves presented here from gamma ray satellites. And one of the takeaway points is now that we argue that gravitational instability in the collapsing star may drive such a variability. The cartoon plot down below is also quite famous. I think many of you have seen it, but it actually shows very nicely the onion-like structure of the collapsing massive star and the fact that we attribute the jet driving the gamma ray burst to the newly formed black hole in this collapse. Our modeling is based on the general relativistic magnetohydrodynamics. The method paper of the code I'm using here was presented in Astrophysical Journal in 2018, and then Dominika used this successfully for her master thesis. So the basic key thing here in this code is the fact that we evolve the GRMHD equations in the changing space-time. So the Kerr metric is described by this G mu nu matrix, which is the 4x4 matrix, and 6 non-trivial coefficients, which are dependent on the mass and spin of the black hole that is the source of gravitational potential. And we are changing this mass and spin according to the TRT and TRV components that are integrated over the horizon of the black hole. The most recent advancement of the code is that we account also for the perturbative terms due to the self-gravity of the collapsing core. So we compute additional perturbative factors and add them to the space-time metric, and they are the stress energy tensors components integrated from the horizon up to the current radius of the shell. These shells here are plotted with the colors on this cartoon. but they are actually representing our layers that are collapsing on the new black hole with time. All the hydrodynamic codes need some initial conditions. So I'm showing here the simplest one we started with. It is the polytropic star described with the equation of state of the polytrope. And this initial condition is posed by transonic solution of a slowly rotating quasi-spherical flow around the curved black hole. We start from the black hole of a moderate spin, and we solve for the profiles of density and radial velocity. And we also form a mini disk in this collapsar due to the inclusion of the specific angular momentum that is dependent on the polar angle. So it is having a maximum at the equatorial plane and is normalized with some value, critical value, which is giving the circularization of the flow at the innermost stable circular orbit. And below and above the toroidal structure, the matter falls supersonically into the black hole, but at the equator, as you can see here, the rotationally supported torus forms, and also it is possible to have outflows, equatorial outflows from such a torus. So here I show the results of the evolution of mass and spin of black hole, which change because of the inflow of rotating massive shells onto the black hole horizon. And in addition, there is this self force in the core that adds the perturbation. So to compare the two effects, I'm showing two different sets of models. The thicker lines are accounting for the self-gravity of the core, and the thinner lines are without this effect. And three different colors represent three different assumptions for the content of angular momentum in the collapsar. So as you can see, the largest number accounts for the slowly increasing mass of the black hole, and also for the highest spin achieved temporarily during the collapse. However, this black hole spins down eventually, and in the end of our simulation, we obtain again a black hole spin of a moderate value between 0.2 and 0.4, while we started from the 0.5 dimensionless spin. What we were interested in were the instabilities in the collapsing core. These are instabilities found at the interfaces. In some regions, there are inhomogeneities in the pressure distribution and in the density distribution. And also they are correlated with the fluctuations of the accretion rate onto the black hole. So these fluctuations are actually interesting from the observational point of view. They should lead to some observable variability effects. And we found that equatorial outflows are stalled as transonic shocks. Here is the analysis performed by Najat Shahamat. She nicely analyzed the Rayleigh-Taylor and self-gravitational interface instabilities in this self-gravitating models. And she found out that the interfacial self-gravitational instability dominates over the Rayleigh-Taylor. The flow is unstable, to remind you, because of the Rayleigh-Taylor instability if the heavy fluid lies on the top of the light fluid, while the other type of instability, the self-gravitational instability, is destabilizing across all the density interfaces. And we found that the growth rates of the self-gravity instability are dominant here. The models which I've shown so far are not magnetized. Now I want to say a few words about the effect of magnetic field. So in some models, we adopted a weak poloidal magnetic field with geometry, either uniform field or a dipole field. Here I present the case of the uniform field of the magnetosphere that has a actually repulsive effect. The configuration was adopted from the classical paper by Walt 74, and you see here on the right a snapshot of the simulation, the repulsive effect of this magnetosphere, which is pushing away the matter from accreting. We also find the magnetically arrested state forming in the accretion flow in the core and facilitating the bipolar jet outflows. These jet outflows are actually temporal So they are not able to break out from our envelope in this simulation. And our black hole spin drops again below A 0.5. So in the end of the simulation, we will not be able to observe the gamma ray burst, but this is a hope with our new simulation. This is a simulation with jet breakout successful. It is the work in progress started recently by Gerardo, and he can show you a nice movie from this simulation. I have only a snapshot where you can see the zoom in part in the left panel and the zoom it out until the scale of 10 to 11 centimeters. We see the magnetized jet breaking out from the envelope. So this is the last slide and the final motivation for our future work comes from the availability of new computational resources, and we also want to plan to study three-dimensional models. Of course, we need much more power, but it is actually interesting to search for non-axis symmetric modes in this instability and plausible conditions for the jet breakouts. Thank you.
Thank you very much. Okay, questions?
Thank you. What are the typical timescale of the jet breakout, considering the jet of the GRB to produce electromagnetic radiation?
This is on the order of 1 second here, this simulation. So I think to the outermost parts, I think, yeah, a couple of seconds. Yeah.
Couple of seconds.
Mm-hmm. And the variability timescales we want to account are down to the milliseconds.
Mm-hmm. Because if you are considering a gamma of 100 or maybe a few hundreds, in that case, it will shorten this time scale by a factor of maybe 500 or so. So that is what we are seeing. And typically, this one should be around 10 seconds at the end.
Mm-hmm. Okay.
Thank you.
Thank you. My question is similar to the question to the previous talk.
Mm-hmm.
In one of your slides, it was written that you used a weak magnetic field. What its value in absolute, in Gausses?
In Gausses, I can't remember now the scaling factors. Yeah, we need to scale to the Gausses, but we normalized this field with the beta parameter initially. So this is the ratio between gas and magnetic pressure, and we are using the value of 10. This is weak. Yeah, stronger would be below 1. Yeah, so very highly magnetized, but this poses some problems to the simulation.
Okay, we move on. Let's thank Aniska again. It's the last two talks of this meeting will go to the stability territory, starting with Max Brill.
I'm going to be moving around too much, probably. Let me set a timer as well. All right, yeah, I'm Max Brill. I'm a postdoc at the University of Geneva, and I'm going to be talking about pair instability of supernovae from a theoretical perspective, and their host galaxies. And this is work with Benji Metha in Melbourne, where we worked on this together. So specifically, since we haven't really talked about pair instability of supernovae, I will cover just a little bit of the theory in very basic terms. So in very massive stars, basically, we reach a regime in the evolutionary phase where the density and pressure and temperature reaches a point where pair creation is possible, and we're starting to form positrons and electrons, which removes the outward pressure. The outward pressure that normally is the radiative outward pressure that's normally there. And so this causes kind of a collapse of the star, and this ignites basically oxygen in the star in an explosive manner and kind of disrupts this whole, the whole star as a whole, if it's massive enough and strong enough. And so observationally, this might be very, very bright given the mass and the that's available. This might be nickel dominated, and this is slowly evolving. And is often thought to exist at low metallicity predominantly because you need to retain enough mass to get such a large helium core for this to occur. And so there's a bit of an elephant in the room for parent stability supernova, and that is that the theory predicts a few to several hundreds of these events per cubic gigaparsec per year, with some dependencies on the internal physics and sort of the metallicity dependence that you assume here. However, the observations have very limited rates. So basically, there is no confident detection, and this sets an upper limit on the amount of parent stability supernovas that we can observe. And so this goes all the way down to 1 to maybe 10 of these events per cubic gigaparsec per year, and there is a whole bunch of potential candidates. If I miss your favorite, let me know and I can add it to it. But there's this contradiction here between the observations and this theory predictions. And so there are basically two components in the theory that can kind of contribute to this, to creating a stellar population and a prediction for this parent stability supernova. The first is sort of what we assume for the star formation history, the metallicity evolution, and then the second is the binary population. So what are the stars doing and what are the formation pathways to these parent stability supernovae? So in this work, we used the TNG simulation to probe at least the star formation history, and we used BPAS, which uses detailed stellar models for the main component in the binary, such that we have a structure of the star so that we can explode this. So let me start with the first component, the star formation history. Galaxies are non-uniform in metallicity. There can be low metallicity pockets in higher metallicity galaxies. And it can be quite a, that's one back. There can be quite a range in this metallicity. And so there are quite a few observations in this regard for this. And this actually makes the problem worse. So these low metallicity pockets can be birth grounds for these massive stars and still produce parent stability supernova closer to basically now, to at lower redshift. And this is what we see as well when we're doing the modeling, when we're including these detailed structures from the illustrious TNG and the detailed metallicity distribution inside the galaxy, we basically get an order of magnitude increase in the parent stability supernova rate at local, the local redshifts. So this is making the problem worse. We don't want this. This is a larger discrepancy, of course. But there is a solution, and of course that's why I'm here. That comes from the binary population synthesis and the light curves coming from this, from the population. So when we, what we try to do is try to determine, okay, what is actually the population we're getting out of the population synthesis, and how observable are these? So we've taken individual light curves and then matched the binary population synthesis models. So try to as closely match the hydrogen envelope and the helium core to the light curve models and weight them accordingly and get actually theoretical light curve rates. So how often each of the light curve would occur over a redshift. And so by doing that, we find that actually 75% of the parent stability supernovae in the population come from 70 to 80 solar mass helium star progenitors, which are explosion energy powered and not superluminous. And so when we convolve this with the observability for two different surveys, so we looked at the Hyper Supreme CAM transient survey and the upcoming Euclid deep survey to check for this rate, if we can observe it, and what the number would be. And for basically for the HSC, we wouldn't have been able to observe it at all, well, 10 to the minus 2, so very rare. And for the Euclid deep survey, we do expect a number of observations, so around 14 a year, if, of course, this holds in the terms of population synthesis. And so 10% of the total systems would be observable. And so kind of, is there an elephant in the room? Not really. We just have to take into account observability as fair is better and make sure that we're doing this matching properly and not say that there is this problem or the difference between the two. And so what kind of effect does this detailed metallicity evolution have on the host of these systems? Basically, what we find is that if you're taking into account the detailed structure of the galaxies, you're shifting it up to higher metallicity. So parent stability supernova hosts are higher metallicity. This, of course, decreases towards higher redshift because then the difference in metallicity of the galaxies is less. Similarly, looking at sort of these host galaxies, and this is at z equals 0, we are seeing that basically they're kind of in more of these dwarf galaxies from a theoretical perspective compared to the core collapse supernova rate here. And so they're less star forming and less massive galaxies. And they're a little bit below the superluminous supernova host, but of course this is a bit hard to do. So therefore it's just a circle. And so this also makes sense because the more massive galaxies have higher metallicities, and there we see that, and you see this effect here. Moving towards higher redshift, we see that the populations start to match up a little bit more, and this continues, this trend continues. And the same is true for the metallicity distribution. The uniform and non-uniform metallicity distributions start to change and become more and more similar. And so my take-home message here, and I'm probably going to be really, really fast here, I see 1 minute left, is that the detailed metallicity distributions increase the parent stability supernova rate quite significantly. But most of these systems of these parent stability supernovae will not be superluminous and would not have been observable, basically. The host galaxies are dwarf galaxies. They're subsolar metallicities for the most part, with low star formation rates compared to superluminous supernova hosts and core collapse supernova galaxies. And the population towards lower redshifts becomes higher redshifts, sorry, becomes more and more similar to core collapse supernova hosts. And I'm happy to take any questions.
Thank you.
Right. So you say these are mostly not superluminous, but can you elaborate a bit on, is there like a typical magnitude we should be looking for, or magnitude range?
So this is a good question. I've believed that from these models, the Carson models, they are more in the core supernova luminosity regime. But yeah, so that's kind of where you want to be looking at, but they are going to be very long duration still. So you need a specific cadence to see them as well.
More questions?
Thanks, Max. So do you have any information about the envelope structure of these stars, whether they are hydrogen rich or hydrogen poor?
Great question. So yes, so this is the nice part about using the B-plus model. So this is basically the hydrogen envelope mass and the helium core mass. And so we've tried our best to match them to the nearest light curve model, what the progenitor was there. And you can see these red colored ones are the ones with hydrogen present. And then these ones are the ones that don't have hydrogen present. So they're pure helium. Now you can see a little blob here, for example, in the models. Those are, sorry, the dots here are the B-pass models with hydrogen present. But the light curve models don't have a good enough like resolution. Basically, there are too few of these models to be able to accurately model this. So these are all matched to the helium core mass, stripped helium stars, but they do have hydrogen on them. Yeah.
We have time for one more question. Anyone online? Okay, no, then let's thank Max again. Right, so next talk and the last one, Ethan Winch.
No, okay. Thanks.
Right, so firstly, I'd like to thank the organisers for giving me the chance to speak here and present the results of present the results from myself and my colleagues. And secondly, I'd like to say how grateful I am that I'm the first person who's going to be talking about parent stability today, and therefore can include a nice detailed slide on exactly how parent stability works. Right, Max? So what am I going to cover? Firstly, I'm going to cover a bit of background, a little bit more into the background of the parent stability and our motivations for why we want to look at this. Then I would like to talk a bit more about MESA, how MESA works, and what we do in MESA. Following this, we'll go into our parameter space and the results that we got from that, and then finish off with a bit of population synthesis just to sort of round off the talk. If you're interested in any of the results, we do have our published paper, which is Winch et al. 2024. The QR code for that is in the bottom right-hand side of this screen. So in terms of the motivation, why are we interested in hydrogen-rich stars and their final fates? Well, part of it is potentially for gravitational wave progenitors. GW 190521 is one that gets brought up a lot in literature because it has very high black hole masses for its components. But there are others that have been more recently detected in GWTC 2.1 and GWTC 3. As well, if we're moving more into the parent stability supernova and the pulsational parent stability supernova, this is where we want to look more at sort of those nuclear synthetic yields. What sort of yields do we get from these models at the end of their lives? And why specifically are we interested in the hydrogen-rich stars? Well, helium stars have been done a lot in the literature. So by exploring specifically the hydrogen-rich models, we can look into the stellar evolution implications of that parameter space. Bless you. Awesome. Okay, so first things first, let's take a look at the instability criterion. This gamma 1, if this is less than 4/3, that represents dynamical instability. What there is meant to be on that top plot there is a nice structure diagram which shows exactly in our models where we get this pair instability. So I would like you to engage your imaginations, and instead I will point out exactly where this happens. So we have, starting from this 10 to the -2, show me I'm pointing out that one, 10 to the -2 here, around here in this core, near the sort of final evolutions of the star, we get this gamma 1 less than 4/3 region. And that is locally dynamically unstable. But how do we determine whether a model is globally unstable? For that, we need to use the global average instability criterion, which is this average, basically the integration over the entire star at a single point in time. That fortunately did appear on the plot, and you can see it is this region here. This drop on the final part here, going below the red line, is where the that pair instability starts happening in the core, and you can see that is what causes the dynamical instability at the end of the star's life. So here's where I would have spent a good minute describing pair instability. However, Max has done a great job for me already. So I'm instead just going to point out on this sketch graph here, up to this boundary here, we get our core collapse to pulsational pair instability boundary. Then you get your pulsational pair instability supernovae, which will eventually stop once you get to your PISN regime, and then you get your photodisintegration, bringing you back to core collapse on the far side. Mostly what I'm interested in right now is this part here. So don't worry, I'm not stepping on anyone else's toes. Now, MESA. Now, most of us have heard of MESA, know it's a 1D stellar evolution code. It is open source and modular, which allows you to customize what physics inputs you want to put in, and allows you as well to create your own physics inputs to go into the code. In terms of exactly how a 1D cell evolution code works, you have these cells which are adjacent to each other. They each have properties, temperature, density, luminosity, etc. They can interact adjacently. And then, of course, if you go to the surface, you can have your mass loss, mass gain, etc. at that point. The parameters we're interested in are initial mass, overshooting, rotation, semi-convection, and metallicity. So overshooting will be that purple region above our convective core, where while the convective acceleration is 0, the velocities might not be 0, so you have that extra mixing that can go on top. And the rotation is also important. You can get a lot more mixing, you can increase the size of your core, and of course metallicity, oh no, wrong one. Metallicity, as has been described, is obviously very important for the winds. I want to highlight that we do not vary the C12 alpha gamma O16 rate, as we are focused on parameters of stellar evolution in this. So our first test was to see if we could find or estimate the final fate of a star without having to model the end of life. We call this the M-crit experiment. There should have been highlights in that plot, but that's fine, I can walk through that anyway. So in this, this is useful for running computationally inexpensive large grids. You only need to run to the end of helium burning in this case, as opposed to the full evolution. And it could also be useful for population studies. At current, however, we can only differentiate between a model which does not undergo pair instability and which does. So it's that first boundary that I was showing on that graph. And what we see, or what you should see, is that actually this value here is consistent across different stellar evolution parameters that we are testing. And so this is the value, these are the values that we get for our critical CO core mass at 36.3 solar masses and our critical helium core mass at 40.6. Moving on, what can we do with these numbers? Well, we can create fits based on these models. Based on a larger grid of models that we run where we're now varying all these stellar evolution parameters. And so in these plots, each data point is a point from the model, whereas each line is a fit we produce based on what we've observed to be the most important parameters for these models. On the top, we are looking at the final mass, at which point we are very interested in the metallicity as highlighted before. And on the bottom plot, we are looking at our core mass, in which case overshooting is now this dominant parameter. Rotation is also important, but we are investigating that in a future paper. Keep a lookout for that one. So zooming in on these a bit more, thank you. On the left, we have our sort of, these are the individual fits. So we have our helium core fit and our final mass fit. And so we can sort of estimate what we'd expect to see as sort of maximum black hole masses for each of these values. This yellow dashed line here corresponding to this green line on here. Going down to 1,000th, that should say 100th, but I'm just going to blame that on the fact that some of my stuff is missing in my slides anyway. Going down to 1,000 Z solar metallicity. Finally, we are moving on to now looking at this sort of population synthesis side of things and a population we can do. For this, we take an IMF-weighted population of 240,000 prospective stars. That is across 8 different metallicity bins and 3 different overshooting bins. We applied the fits that we had on the previous slides, and we get these estimates of a potential black hole population. From this, we can see the contribution from different metallicities, different overshootings, stellar parameters in general, into the final into these final masses of these stars. And if I go ahead, there we go. We can see on this one what the overshooting now looks like, where you see you get the high overshooting really cuts down your sort of a black hole mass, but that low overshooting can push you up a lot higher when you have these masses. So when you have this hydrogen-rich envelope. So with that, I will bring myself onto my conclusion slide. Thank you very much for your attention.
Thank you, Ethan. Any question? No question? Okay. I have one question. So these stars will still have lots of hydrogen at the end of evolution. So you think they can be progenitors of type 2 superluminous supernovae, the hydrogen?
So I believe there's people in this room who are a lot better at talking about superluminous supernovae than myself. However, I suppose yes, because they're still relatively compact. So a lot of that hydrogen won't just disappear. It will still be there for whatever happens in the end of life.
Okay, thanks. So
thanks for the talk. What is your efficiency of black hole formation at these high masses? Like how many do go into that?
So we do not calculate down to the end of life with the actual collapse scenario. As well, there's also a lot of different things that can happen in terms of what happens to the masses it's falling in. like, magnetic field dependent, rotation dependent. So I can't really give you an answer on that. Well, actually, no, I can. It's just that the efficiency right now is 100.
Okay. Full fallback, basically.
Yeah,
Cool.
assuming full form.
Thanks.
Thank you.
Wait, any more?
Hi. How do you determine whether a black hole forms in your models?
So that is our critical core masses that we have. So for the moment, we just say if it doesn't undergo PI, it's a mass in our star, assuming the core collapse scenario. If it's above that, then it'll have some form of PI, so we exclude it for now. But of course, you would get the pulsational pair instability. From what I see in the literature, you'd still get some higher mass black holes before you get to that final sort of cutoff point, which I show. I can't go back to it right now. Yeah, so you'd still get some black holes further on from what we show, but what we show is basically just all assumed black holes.
Okay, one last chance for question. No? Okay, let's thank again. All right, so sadly we've come to the end of the focus meeting. I hope it's been useful, and I would like to thank everyone again here and online for all the contributions. Let's give a hand. And yeah, so thank you so much, and hopefully see you in the next conference.